Knowledge Academy. The main of this lecture is to discuss about the digital electronics concepts in a very detailed manner. And if you like the content of the channel, then please to like, share and subscribe to the YouTube channel and don't forget to press the bell icon button. So whenever you upload new video, the direct notice comes to mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely do one good improvements in the coming lectures. So what do we let's get started. The first concept that we are going to learn in the digital electronics is always called as the Boolean algebra. So Boolean algebra is the basic concepts that we need to learn in the digital electronics. So we will discuss about the Boolean algebra. So in the Boolean algebra, we have three basic operations which is called as the AND operation, OR operation and the NOT operation. See, AND operation means we are going to represent by symbol of dot, and for our OR operation we are going to represent by symbol of plus. And NOT operation means we have to represent by symbol of bar. So now we can see clearly for each and every aspect that now we are going to learn in a detailed manner. Listen carefully. AND operation. AND operation means basically 0, and we can say 0 and 0 is equal to 0 and 0 is always equal to 0. 0 and 1 is equal to always 0. 1 and 0 is equal to 0. 1 and 1 is equal to 1. So 0 and 0 is always equal to 0. 0 and 1 is equal to 0. 1 and 0 is equal to 0. And 1 and 1 is equal to 1. Same thing, A dot A is always equal to A. A dot A bar is always equal to 0. And A dot 0 is equal to 0. And A dot 1 is equal to A. So this is something that we always have to keep in mind regarding the AND operation. See, AND operation we can call it as the dot also, we can say like this, or AND, everything is same. So therefore here 0 and 0 is equal to 0, 0 dot 1 is equal to 0, 1 dot 0 is equal to 0, 1 dot 1 is equal to 1. Similarly, A dot A is equal to A dot A bar is equal to 0, and A dot 0 is equal to 0, and A dot 1 is equal to A. See, no matter how many times you do the AND operation for the same symbol A, same thing that you are going to get, which is A dot, A dot, A dot, A dot, up to each time it is always equal to A. So if you multiply, if you do the AND operation with respect to 0 of anything, always it is going to give you 0. Here A dot A bar, if 1 is 1, the other should be always 0 because it is a dot, the bar is there, so it is always equal to 0. Similarly here also each and everything that you can see clearly. So 0 dot 0 is equal to 0, 0 dot 1 is equal to 0, 1 dot 0 is equal to 0, and 1 dot 1 is equal to 1. A dot A is equal to A dot A bar is always equal to 0, and A dot 0 is equal to 0, and A dot 1 is equal to A. So now we discuss another operation which is called as the OR operation. OR operation means we are going within the symbol of plus. So 0 or 0 is equal to 0, 0 or 1 is equal to 1, 1 or 0 is equal to 1, 1 or 1 is equal to 1. Similarly, A or A is always equal to A plus A or 0 is equal to A or 1 is equal to 1, A or A bar is always equal to 1. So these are the things that you always have to keep in the mind. So 0 or 0 is equal to 0, 0 or 1 is equal to 1, 1 or 0 is equal to 1, 1 or 1 is equal to 1, A or A is equal to A or 0 is equal to A or 1 is equal to 1, A or A bar is always equal to 1. So this is the thing that you always have to keep in your mind. Now, NOT operation means it is a, we are using the symbol of the bar, so therefore 0 bar is equal to 1 and 1 bar is equal to 0. So these are the three important things that you always have to keep in your mind. So with these basic concepts that we can move further to learn each and every concept in the digital electronics. So now I will discuss about the important formulas, which is A or B dot A or C is always equal to A or B into C, B dot C. See, A or B dot A or C is always equal to A or B C. So this is a very important formula. Listen carefully. Here A or B dot A or C. A or B dot A or C is always equal to A or B into C. See, basically, here A also is A. So write C into A. Here write R. And it is a B here, it is C here. Just you have to multiply with these two things. So B, C. So A or B dot A or C is always equal to A or B into C. So A or B dot A or C is always equal to A or B into C. It's a very important formula. So A or B dot A or C is always equal to A or B into B dot C. Similarly, A plus B, A or B is always equal to A plus A bar B. A or B is always equal to A A or A bar B. So A plus B, A or B is always equal to A plus A bar B. So A plus B is always equal to A plus A bar B. So very important formula. So these are what are the formulas that I am going to discuss now. These are very much important in doing the simplification of the K max and the simplification of larger number of equations. So A or B, A plus B is always equal to A plus A bar B. It's a very important thing. A plus B is always equal to A plus A bar B. Similarly, AB plus A bar C plus BC is equal to AB plus A bar C. AB plus A bar C plus BC is always equal to AB plus A bar C, because you can see here there is A, here there is A bar. Here B, here C. Then we have do that, multiply of these two things, then we are going to get BC is equal to, just to have taken the first two things for the third thing. So AB plus A bar C. So this is a very important thing that you always have to keep in your mind. So AB plus A bar C plus BC is equal to AB plus A bar C. So AB plus A bar C plus AB plus BC is equal to AB plus A bar C. So AB plus A bar C plus BC is equal to AB plus A bar C. It's a very important formula. Suppose if you do the reverse of this one, if you do the reverse of this, see B plus plus by dot and dot B plus, you are going to get this relation which is A or B dot A or C dot B or C is equal to A or B dot A or C. So basically this is called a duality. Duality means what we are doing, duality means changing the plus to dots and dots to plus. So this is the code that you always have to remember. So duality, it is the duality theorem. So therefore A or B dot A bar plus C dot B plus C is always equal to A plus B dot A bar plus C, because I will interchange the plus to dot and dot to plus. So I am going to get this equation. So this is called the duality, means we can say it is a dual of this one. Always the dual is always equal. Same thing we are going to get, which is A plus B dot A bar plus C dot B plus C is always equal to A plus B dot A bar plus C. So this is a very important point that you always have to keep in your mind. So now here there is A bar B, A plus B dot A bar plus C is equal to, just you have to do the product of these two things, AC plus A bar B. So here you have to multiply these two things and these two things, then you have to add this one. So A plus B into A bar plus C is always equal to, just you have to multiply these two things, A into C plus B into A bar, or A into A bar into B. So it will be same. So here it has to be A, here it has to be you can say complement of this one. So A plus B dot A bar plus C means you have to multiply these two things and then you have to multiply these two things and keep the plus. So you are going to get both as same. So these are the four things that you always have to keep in your mind, which is here A plus B into A plus C is always equal to, here I already told you, here A, here is A. So keep here A plus. Then multiply these two things, we are going to get B into C. So A plus B into A plus C is equal to A plus B into C. Similarly, A plus B is equal to A plus A bar B. I already told you that AB plus A bar C plus BC is always equal to AB plus A bar C plus BC is equal to AB plus A bar C. Just do the dual of this one. So A plus B dot and dot B plus, we are going to get A plus B dot A bar plus C dot B plus C is always equal to A plus B dot A bar plus C. Similarly, there is A plus B dot A bar plus C means you have to multiply these two things and these two things and keep the addition. So AC plus A bar B. So these are the very four things, are basically five formulas which are very much useful in solving the complex equations. So A plus B dot A plus C is equal to A plus BC. A plus B is equal to A plus A bar B. AB plus A bar C plus BC is equal to AB plus A bar C. A plus B dot A bar plus C dot B plus C is always equal to A plus B dot A bar plus C. Similarly, A plus B dot A bar plus C is equal to AC plus A bar B. So these are very important formulas. And now I told you A XOR B is equal to A XOR B is equal to A bar B plus A B bar. You can write it in another fashion, which is A plus B into A bar plus B. I have already told you if it is in this format. So this is in this format. You have to multiply these two things and these two things, and you have to add. So which is A into B bar plus A bar into B. Same principle that you have to use the previous one. So A XOR B is equal to A bar B plus A B bar is equal to A plus B into A bar plus B bar. So therefore these two things you have to multiply and these two things you have to multiply. You are going to get this result. That is A into B bar plus A bar into B. Similarly, A XOR B whole conjugate, we can say A XOR B whole conjugate is called as the A XOR B, or simply we can write A XOR B is always equal to AB plus A bar B bar. AB plus A bar B bar is equal to, you can write like this, which is A plus B bar into A bar plus B. So you have to multiply these two things, A into B plus A bar into B bar. Similarly, A into B into C whole complement is equal to A bar plus B bar plus C bar. So A into B into C whole bar is equal to A bar plus B bar plus C bar, and A plus B plus C whole bar is equal to A bar into B bar into C bar. So these are the very important formulas which are definitely used in digital electronics in a wide range. So therefore A XOR B is equal to A bar B plus A B bar is equal to, which is A plus B into A bar plus B bar, because we have to multiply these two things and these two things we are going to get this result. A XOR B one complement is equal to A XOR B is equal to AB plus A bar B bar is equal to this A plus B bar into A bar plus B. So A into B plus A bar B bar, and A into B into C whole bar is equal to A bar plus B bar plus C bar, and A plus B plus C whole bar is equal to A bar into B bar into C bar. So these are the important formulas which are definitely used in the digital electronics. So let me repeat this one here. Finally, A plus B dot A plus C is equal to A plus B into C. A plus B is equal to A plus A bar B. A into B plus A bar C plus B C is equal to AB plus A bar C. A plus B into A bar plus C into B plus C is equal to A plus B into A bar plus C. And here A plus B into A bar plus C, and only to multiply the corresponding and do the multiply this corresponding and do the addition. So AC plus A bar into B, A XOR B is equal to A bar B plus A B bar is equal to A plus B into A bar plus B bar. Multiply these two things and multiply these two things and do addition, we are going to get this result. And A XOR B whole complement is equal to A XOR B is equal to A into B plus A bar B bar is equal to, which is A plus B bar into A bar plus B. So we have to multiply these two things, AB plus A bar B bar, and A into B into C whole bar is equal to A bar plus B bar plus C bar. A plus B plus C whole bar is equal to A bar into B bar into C bar. So these are the important formulas which are regularly used in the digital electronics. So now we'll discuss some of the Venn diagrams in the digital systems. It's a very important concept which is called as the Venn diagram in the digital systems. So now we'll discuss the Venn diagrams in the digital systems. The concept of Venn diagrams in the digital systems. So you can see clearly this is the Venn diagram. So this is the A and this is the B. So there is the interaction between them. So we are going to represent this area. So we are going to represent this area by, which is A bar, this A into B, or A dot B. So therefore this we are going to represent this area, we are going to represent by a symbol which is called as the A dot B. So A into B or A dot B. So whatever this graph is, we can say the common region we are going to represent by a symbol which is called as the A dot B. Similarly, suppose there is another Venn diagram, you can say C, A, B. But we want whole thing. So we want whole thing means we must do like this, which is, listen carefully, this not this area. So this area is nothing which is A dot B bar. So this area is called as the A dot B bar. So this area is called as the A dot B bar. And this is A into B, and this is here B into A bar. So B into A bar is this area. So if we add all this each and everything, we are going to get total B. Therefore, just to addition, A dot B bar plus A into B plus A bar dot B. So if you do addition of these two things, of all these things, finally we are going to get A or B. So we can write either in this fashion or in this fashion, which is same, which is A or B. So therefore, A dot B bar plus A into B plus A bar dot B is equal to A plus B. So everything is going to become A plus B, A or B, or A plus B or A or B. So A plus B we are going to get which is 1. Similarly, here, suppose if you see clearly, there is another type of Venn diagram. Here there is a and this is a B. Say I want only this one, but not this one. I want the region is covered by like pencil like this and run a graph. So what is this area? What is this? We are going to consider, which is, you can see clearly here, this is see, I want this area. What is this area is nothing but here. I already told you. This area is nothing but A bar dot B. This is called as A bar dot B. This area is called as A bar dot B. And this remaining black area, the remaining black area is equal to A or B whole bar. A or B whole bar, we are going to get this area. So A or B whole complement, or you can say A or B whole complement, we are going to get this area. So if you want these two things, just you have to do the addition, which is, this is called as the A dot B bar. A bar dot B, this is called as A bar dot B, and this is A or B whole bar, A or B whole bar. So I want both the things, just do the addition of these two things, finally we are going to get A bar. So simply we can say this is equal to A bar. You can say clearly, this is called as the A bar. This is A, this also it's called as the A bar. Similarly, you can see clearly there is another Venn diagram, which is three circles we are going to see, there is a intersection between them. So I want these three things. What is this? We are going to represent in terms of digital electronics. So you can see clearly here, this is called as the A into B C bar, A, B, C bar, A into B into C bar. So A into B into C bar, only this area is called as the A into B into C whole bar. A into B into C bar, and this is called as the B into C into A bar. So B into C into A bar. And this is called as the basically A into C into B bar, A into C into B bar, A into C into B bar, and this is called as the A into B into C. So A into B into C. So you can see clearly this is called as A into B C bar. This is ABC. This is called as the A into C into B bar, and this is B into C into A bar. So if you add all these things, we are going to get like this, which is AB plus BC plus CA. AB plus BC plus CA, you are going to get like this, which is AB plus BC plus CA. If you do a simplification of this complex expression with the help of K naught or simply the normal we are doing, finally we are going to get AB plus BC plus CA. Suppose there is another type of Venn diagram, you can see clearly there is another type of Venn diagram. So these are the three circles. So this is A, B and C. I want only this area, which I am going to represent here. So this area I want to do. But here, this total area is called as the A. This total area is called as the A. This total area is called as the A. And this is basically I already told you, which is B into C, A bar. So simply we can get A bar into B into C. If we do addition of these two things, we are going to get overall thing. If we do simplification, we are going to get A plus BC. I already told you A plus A bar B is equal to A plus B. So with the help of the basic principle, we are going to get A plus BC, because A plus A bar B is equal to A plus B. So with the help of conjugate, so we are going to write as B, we are going to get A plus BC. So this is the thing that you always have to keep in your mind. So this is basically the simplified expressions for this representation. So Venn diagrams in digital system, this is called as the A dot B and A into B. And this is what I told you, A into B bar plus A into B plus A bar into B. Simply A bar A. Here I only told you this area is called as the A into B bar. Sorry, B into A bar, and this is called as the A or B and bar. Then we are going to get A bar, just simply A bar. I only told this one, for this one, here you can see there are three circles. This column area I already told you, this is A into B, C bar, here ABC, and this is called as the B into C, A bar, and this is A into C, B bar. If you have all these things, you are going to get AB plus BC plus ACA. And for this one, I already told you, this area is A, and this is A bar into B into C. So if we simplify this one, we are going to get A plus A bar, A plus BC. So A plus BC that we are going to get. So these are the one-dimensional digital systems, and these are the corresponding representation for this graphs that I already shown you. We are going to discuss about another new concept which is called as the switching functions. Means we are going to add the switches, and then we will see what is the nature of the bulb, whether it is on or whether it is off, that we are going to see here. So you can see clearly here, this is there is a one switch. So there is a one switch here. We are going to keep the source voltage, and we are going to keep the bulb in this fashion. So you can see clearly the switch is covered in series fashion with respect to bulb. See now I want to see what is the nature of the output bulb I want to see here. So you can see clearly here. So suppose A is equal to 0 means it is off. A is equal to 0 means the switch is off. If A is equal to 1 means the switch is on. Similarly, the bulb, if it is off means 0, bulb on means 1. So this is the thing that we are going to use here. 0 means the switch is off. A is equal to 1 means the switch is on. Y is equal to 0 means the bulb is off. Y is equal to 1 means the bulb is on. So now, suppose if I open the switch means whenever the switch is open means 0, then there is no current, so bulb is going to get off, so Y is also equal to 0. Suppose if I on the switch, then the current is going to flow, so bulb is going to get on. So if A is equal to 1, it is on, then the bulb is also going to get on. So therefore, same thing, it is also 1. So Y is always equal to A. So you can see clearly Y is equal to A. So this is what I am trying to tell you. So whenever you connect a current series, whenever you connect a switching series with respect to bulb, then Y is always equal to A. So now suppose there is another, so suppose if I am going to connect the switch in the parallel with respect to bulb, and then I will see what is the nature of the output I want to see here. Same thing here, I already told you, whenever the switch is on, means whenever the switch is on means A is equal to 1, switch is equal to off means 0, bulb is equal to on means 1, bulb is equal to off means 0. So you can see clearly here, I have drawn this graph, I have drawn this table. See, whenever the switch is off means 0, then the current is going to get flow and the bulb is going to get on. So Y is equal to 1. Suppose the switch is closed, means A is equal to 1, then this adding the load resistance when compared to bulb. So all the current will flow to the switch but not to the bulb. So bulb is going to get off. So Y is equal to 0. You can see when A is equal to 0, Y is equal to 1. When A is equal to 1, Y is equal to 0. So you can see clearly both are complement. So output is always complementary of input. So Y is equal to A bar. So Y is equal to A bar. Whenever you count in series, Y is equal to A. Whenever you count in parallel, it is complement. Y is equal to A complement or A bar. Suppose if I count the two switches in series, then I want to see what is the nature of the output I want to see here. So you can see clearly here. So you can see clearly here, this is the switch A, this is the switch B, and this is the output Y. So whenever the switch A is open and B is open, whenever the both are open, then definitely you are going to get the bulb is off. If the switches A is open and B is on, then definitely you are going to get again 0. If switches A is on and B is off, again you are going to get 0. If both are on, then the bulb is going to get on. So this is what Y is equal to. Here you can see clearly, then we are going to get which is Y is equal to A into B, because 0 into 0 is 0, 0 into 1 is equal to 0, 0 is equal to 0, so 1 to 1 is equal to 1. So this is basically for AND gate. So therefore Y is equal to A dot B. So what I am trying to tell you is very simple. Whenever you connect the switches in series, one should be on, then the bulb is going to get on. If at least one is open, definitely we can say the bulb is always off, means 0. See, the switch is equal to on means it is 1. Switch is equal to off means 0. Bulb is equal to on means 1. And bulb is equal to off means 0. So this is the concept that you always have to remember. So whenever you connect the switches in series, you have to use the dot product, which is Y is equal to A dot B. A dot B. So this is the concept that you always have to understand. can see clearly this is basically a circuit. So now I am going to cut in a parallel fashion. So these two switches in series, but they are parallel in the, with respect to bulb. Then what is the thing? So just to the complement of the previous one. So this is basically A dot B. So this is A dot B whole bar. It's a complement that you have to take always. So you can see clearly A, B and Y. If A is off, B is off, then no current is passes through bulb. So the current is going to pass through bulb, so bulb is going to get on. If A is off and B is on, again current to the switch is 0, so current is always going to flow through bulb, so bulb is always on. If A is equal to on and B is equal to off, so if you on the switch A and if you on the switch B, then definitely current passes through this bulb, so bulb is going to get on. If I close both these switches, then no current passes through bulb, so bulb is going to get off. So this is the A dot B whole bar. So A dot B whole bar, we are going to get this is the equation for this A dot B whole bar. Similarly, suppose if I connect the switches in parallel, if I connect the switches in parallel with respect to, again they are in series with the bulb, then what is the output equation? Here, if any one is closed, definitely the bulb is going to get on. If any one is closed, the bulb is always going to get on. If both are open, then only the bulb is off. So you can see clearly, if both are off, again bulb is off. If any one is closed, bulb is always equal to on. You can see here B is closed, so bulb is on. Here A is closed, the bulb is on. Here both are closed, so the bulb is always the bulb is on. So if both are open, then only the bulb is off. Otherwise, you are always going to get down with the bulb. So Y is always equal to A bar B. So you know that in parallel means A bar A, A or B, A or B you are going to get. Suppose if I keep the parallel is in like this now. Suppose if I keep in parallel with respect to bulb, again just whatever the equation that you are going to get previously just with the complement. So A bar B, whole bar you are going to get. If you want to see the equation, then you can write a truth table and you are going to get the same thing. A, B and Y. If both are off, means the current flows through bulb, so therefore bulb is on. If any one is on, then the bulb will never glow. If anyone is on, the bulb will never glow. So if anyone is on, the bulb is never glow. If both are open, then the bulb is going to get on. So this is the truth table that we are going to, which is equal to ARB whole bar. But here, if you take the other combination here, these are in parallel and these are in series, and it's all in series with respect to bulb. I already told you this combination is ARB, and this is whenever they are in series, you have to keep the dot. So therefore, ARB dot C. So this is the equation that we are going to get for this bulb. So Y is equal to ARB dot C. If you want to check this one, you can write the truth table and you are going to get the same equation. See, if A on, C on, then only bulb will on. If B on, C on, then definitely bulb will on. Otherwise, here, then definitely in the remaining cases, if A, B on and C on, then remove the bulb ons. Only at these three conditions we are going to get the bulb is on, and at remaining one of the conditions we are going to get the bulb is off. So we can see clearly only in three conditions the bulb is on, and remaining all conditions the bulb is always off. So if A is on, B is off, C is on, then definitely when A is on, C is on, definitely you are going to get the bulb is on. If B is on, C is on, then definitely you are going to get bulb is on. If A, B and C are on, then definitely the bulb is going to get on. And except these three conditions, in the remaining three conditions, the bulb is always off. So therefore, Y is equal to ARB dot C. So this is the equation that you are going to get. So these are the different equations that we are going to get for different cycle diagrams. So whenever this is in series with respect to bulb is Y is equal to A. If it's a parallel, just to the complement, Y is equal to A bar. If both are in series with respect to bulb is Y is equal to A dot B. If they are in parallel, whenever series in parallel is A, Y is equal to A dot B whole bar. If they are in parallel like this means Y is equal to A or B. But if they are kept in parallel, again parallel with respect to bulb means Y is equal to A or B whole bar. Again, if you see like this is series combination with respect to bulb. This is parallel and this is series, overall series, so ARB dot C. So finally I can say that whenever the switch is in series with respect to bulb, then Y is equal to A. If it is in parallel with respect to bulb, means complement, Y is equal to A bar. If both the switches are in series and they are also series with respect to bulb, means Y is equal to A dot B. If the switches are in series but they are parallel with respect to bulb, means Y is equal to AB whole bar. If both the switches are in parallel and they are in series with respect to bulb, means Y is equal to A or B. If both the switches are in parallel and when they are parallel with respect to bulb, means Y is equal to A or B whole bar. if the both switches are in parallel means A or B and they are in series with respect to C means A or B dot C again it is in series with respect to bulb. So finally equation is equal to Y is equal to A or B dot C. So this is the equation that we are going to get. So series with respect to bulb means always you have to do the dot product. If they are in parallel means keep the bar. So if they are in series, if the switches are in series with respect to bulb means simply we can skip the equation. Just parallel means keep the bar. So this is the concept. When they are in series with respect to the switches are in series means A dot B. If they are in parallel means A or B. So this is the concept that you always have to understand. So now other concept in here which is diodes in digital. So what are the, we can say how we are going to using the diodes in the digital electronics we are going to discuss now. Suppose there is a diode here, you can see clearly there is a diode here. Here this is called as the anode and this is called as the cathode. The anode I am given to 5 volt and the cathode I am going to give to 0 volt. So we can say the anode is at the higher potential with respect to cathode. So it is going to give in the forward bias. So it is going to become active short circuit. So we are going to the short circuit. It is called as a forward bias because the anode voltage is higher than cathode voltage. So it is going to basically on means we are going to get in short circuit. It is called as the forward bias. Suppose if I keep the anode voltage to 0 and the cathode voltage to +5, so therefore the cathode voltage is higher than the anode voltage. So this diode is going to get off. So this called as the reverse bias means open switch. So we have to read something like open switch. It is called as the reverse bias. Suppose if I give for this diode, the anode is at the +5 volt and the cathode is also +5 volt. So if you give in this format, in the digital electronics, we are going to assume it as the open circuit because it is also called as the unbiased. It is not given a proper biasing, so we are going to assume that it is in the open state. It is always in the open state. It is called as the unbiased. If you give identical voltage across the P or N of a diode, then we are going to assume this basically at the open state. So this is called as the unbiased. If anode potential is greater than cathode potential, we are going to assume the switch is at on, this called the forward bias. If the cathode potential is greater than the anode potential, then we are going to call this as the reverse bias means the switch is off. That is off means it's like open circuit. Suppose if the diode for anode and the cathode if you give identical voltage, we are going to assume it as the open circuit means it is off switch means we are going to call this as the unbiased means the biasing is not given proper, so this is called as the unbiased. So this is the thing that you always have to understand. So this concept that we are going to use in the digital electronics to solve the numericals based on the diodes. So let me tell you another concept which is called as the duality. So duality means here, basically let me tell you in detail regarding the duality. Suppose for the positive logic we are going to assume for high voltage, for high potential we are going to assume this logic 1 and for low potential we are going to assume it as the logic 0. For negative logic it is the reverse of this one. So for low potential, so we can say for high potential we are going to assume it as the logic 0 and for the low potential we are going to assume as logic 1. So for high potential we are going to assume it as the logic 0 and for low potential we are going to assume it as the logic 1. So reverse of this one. So for positive logic we are always going to assume high voltage means logic 1, low voltage means logic 0. For negative logic means for high potential we are going to assume this logic 0 and for low potential we are going to assume this logic 1. So this is the reverse of this one. So for positive logic means for high potential logic 1, low potential logic 0. For negative logic means reverse of this one. For high potential logic 0 and for low potential logic 1. So now we are going to discuss for general here. Suppose there is a function in this format. Suppose there is a function, it is having a bar dot plus 0 1. Dot means and plus means or. Suppose if I apply the duality on this function, then do not change a and a bar. Just to change the dot to or to dot, 0 to 1 and 1 to 0. So never change the a and a bar. So never change the, you can say the values, do not change the a or a bar. It will remain as it is. So a and a bar is same. Just replace it. Just represent dot by, or you can say and by or by and 0 by 1 and 1 by 0. So this is a concept that you always have to remember. So if you apply the duality, never change a, never change a bar. Just change the and to or to and 0 to 1 and 1 to 0. So this is called as a duality. So this is the duality principle. Means if you are going to apply the duality, never change A, never change A bar, just change the AND to R to 1 and 0 to 1 and 1 to 0. See, duality, if duality, again if you do duality, again you are going to get the same function. Suppose for a function if you do the duality, and if you again apply the duality, same function that you are going to get. So this is the basic thing. For a given function, if you do a duality, and if you apply duality again, then you are going to get the same function. Suppose if the duality of the function is equal to function, then f is said to be self-dual. Means if the duality of the function itself is equal to f itself, then we can say that function is said to be self-dual. Means the duality of the function is equal to function itself, then the function is said to be self-dual. So now suppose if I apply the duality of AND gate. AND gate means A dot B. So if you apply duality, you are going to get A or B, which is equal to OR gate. And if you apply for NAND gate means I already told you, NAND gate means A dot B whole bar. If you apply this one, then what you are going to get A plus B whole bar. A plus B whole bar is called as the NOR gate. So we are going to get this one. Similarly for XOR, if you apply duality, you are going to get XOR. For NOT gate, you are going to get the same thing, NOT gate. For buffer, you are going to get the same thing, buffer. Buffer means like A. If you apply duality, again you are going to get the same thing, A. So therefore, we can say that here, for AND gate, you are going to get the OR gate. Vice versa is also true. For AND gate, NOR gate, for OR gate, AND gate. For NAND gate, NOR gate, and NOR gate for AND gate. So vice versa is also true. So for XOR, you are going to get XOR. If you apply on XOR, you are going to get XOR. So NOT is not, buffer is buffer. So this is the concept that you always have to understand. So if you apply the duality, never change the A, never change A bar, just change the AND gate to AND to R to AND, 0 to 1 and 1 to 0. So this is the concept that you always have to remember. The duality of the function, if you apply the duality 2 times, you are going to get the same function. If the duality of the function is equal to F, it is said to be a self-dual. So for AND gate, OR gate, you are going to get, for NOT, you are going to get NOR gate. For XOR, you are going to get XOR. For NOT, you are going to get the same thing, NOT. For buffer, you are going to get the same thing as buffer. Vice versa is also true. Suppose if you apply the complement, then what is going to happen? So you can see clearly, if you apply the complement, then what is the thing that we have to do? See, complement means for a given function, if you apply the complement, then change A to A bar to A, dot by plus by dot, 0 by 1 and 1 by 0. So this is the concept that we always have to understand. If you apply the complement on a given function, change A to A bar to A, and dot to plus to dot, and 0 to 1 and 1 to 0. So this is a concept that you always have to understand. So therefore, whereas in the duality, we are not changing A and A bar, but here we have to change even A and A bar also. So this is a concept that you always have to keep in your mind. So in duality, never change A or A bar, keep as it is. Whereas in the complement, change A also and A bar also. Change A to A bar and A bar to A, and the remaining thing is same as the duality. So therefore, the complement of a given function, if it is having all these parameters, then we have to change A to A bar to A, and dot to plus, and place to dot, and 0 to 1 and 1 to 0. So like this that we are going to get. So now let me tell you regarding the SOP and the POS representation. SOP and the POS. SOP is called as a sum of product, and POS is called as a product of sum. So listen carefully. Here SOP is called as a sum of product, and POS is called as a product of sum representation. Suppose let me take 3 variables A, B and C. So with 3 variables we are going to get 8. You can see 8 values we are going to get, which is for n variables we are going to get 2 to the power of n combination. So for n variables we are going to get 2 to the power of n combination. So as a 3 at the end, so 2 to the power of 3 is equal to 8. So 8 combinations that we are going to get. 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 So like this that we are going to get. So I already told you, so there are two things that we always have to understand, min term and the max term. Let me tell you, the first thing is called as the SOP representation. So this is 0, decimal format, this is 0, M0, M1, small. In the SOP always we have to use the small letters M. So M0, M1, M2, M3, M4, M5, M6 and M7. These are basically in the decimal formats. So now in the SOP means always you have to use the small letter of M. It is called the mean terms. Mean terms means small m. Then here, see, this is, so just do this one, which is 0 means, whenever there is a 0 means represented by A bar, complement. If there is 1 means take the number, take the letter as it is. If there is 0 means just do the complement of that letter. If 1 is there means keep as it is. So 0 means to the complement A bar, here B bar, here C bar. So A bar, B bar, C bar, just do the multiplication. For this one, we are going to get A bar, B bar, C. Here this is A bar, B, C bar, and this is A bar, B, C, and here it is A, B bar, C bar. Here A, B bar, C. Here A, B, C bar, A, B, C. So whenever there is a 0 means just to the complement of that letter. Whenever there is 1 means keep the letter as it is. Just to the product of the letters. We are going to get this is called as a main term. This is the main terms. So this one we are going to get A bar, B bar, C bar, A bar, B bar, C, A bar, B, C bar. Here we are going to get A bar, B, C. This is A, B bar, C bar. This is A, B bar, C. Here A, B, C bar, A, B, C. So these are the mean terms that we are going to get. Total 8 mean terms you are going to get here. So now let me tell you the mean terms again. See, in the mean terms there will be canonical SOP form. Canonical SOP form is you are going to get all the, we are going to get a very complex equations for each and every one. So for each and every one, whatever the, suppose if the output was for certain combinations you are going to get 1, then we have to do all, we have to add all these mean terms. Then that is called the canonical SOP form. So listen carefully. See, for a given, suppose for certain combinations the output will be 1. So you have to add all those output equations. All those output equations that we have to add. You have to do the basically sum. So it is called the SOP, sum of product. So therefore we can say if you add all those things, you are going to get a canonical SOP form. It's a very complex expression. So by using the simplifications, if you do a very small equation, you are going to get a minimal SOP form. So if you do certain methods, we can reduce that to a very simple form. It is called as the minimal SOP form. And then you can write in terms of the standard SOP form. So standard SOP form is going to give you the representation of each and every one we are going to get. So for canonical, see, canonical means for each and every one you have to do the addition of all the mean terms. This is called the canonical SOP form. So if you do simplification with the help of small techniques that you will learn. So now if we apply those techniques, whatever the simplified expression it is called as the minimum SOP form. And standard form is nothing but it is a standard representation. It is going to give you where the output is always equal to 1. So we will discuss each and everything. So therefore always for 1 we are going to see. Now we will discuss about the max terms. Max terms means I already told you here in the min terms means smaller, in the max term is capital M. So capital M 0, capital M1, capital M2, capital M3, capital M4, capital M5, capital M6 and capital M7. So now just do the complement of this one. Just do the complement of this one. I already told you replace A, if A bar is there means just do the complement A, B bar means B, C bar means C. So just do the addition. So just do the addition. Means we are going to basically do the complement of all these mean terms. If you do the complement of all these mean terms, then we are going to get the max terms, which is A plus B plus C, A plus B plus C bar, A plus B bar plus C, then A plus B bar plus C bar, A bar plus B plus C, A bar plus B plus C bar, A bar plus B bar plus C, A bar plus B bar plus C bar. So these are the max terms that we are going to get. If we are complement of the corresponding min term, then we are going to get the max term. I have already told you complement means replace A by A bar by A, and I have already told you dot by plus by dot, 0 by 1 and 1 by 0. So if you apply the complement of corresponding min terms, you are going to get the max terms. So this is the very important thing that you always have to keep in mind. So if you do a complement of the corresponding min term, you are going to get the max term. Then here always for 0. So wherever the output is 0, suppose for a given 7 combinations, you are going to get the output as 0. Only those terms that you have to take, only those max terms you have to consider, and you have to do basically the product you have to consider. So here we have to do the product of all those max terms you have to do. So that is called as the product of sum. So product of sum, that is called as the POS. So if you do product of all those max terms, for corresponding 0, It is called a canonical POS form. So if you apply the techniques and if you simplify, finally we are going to get a certain minimal, we can say very simple expression which is called as a minimal SPOS form. Now what I told you, standard POS form is going to represent wherever the max terms as 0. So wherever the output is 0, where it is going to tell you. So this is called standard POS form. So always for max terms means 0, in terms means 1. So this is a very important concept that you always have to understand. Now we will discuss about the one more insert. So now we will discuss about one more important concept which is called as the logic gates. See, now we will discuss each and every gate which is going to use in the digital electronics. The first is called as the NOT gate. NOT gate means basically we are going to get like this, which is called as this is the symbol of a NOT gate. If input is A, then output is equal to complement of the input, which is Y is equal to A bar. If input is A, the output is always equal to A bar. So this is the symbol of a NOT gate. So let me give you the truth table of this NOT gate. This is A, this is A and this is Y. It is the input and this is the output. If input is equal to 0, the output is equal to 1. If the input is equal to 1, the output is equal to 0. Both are complement of each other. So output is the complement of the input. So let me draw the circuit diagram of this one. So inside how it is going to be like this. Inside we are going to have a transistor and resistors. So this is the input resistor and this is the resistor here. So this is the output Y. Y is equal to, you can see clearly, when A is equal to 0, this is open. So whatever the input voltage is across this one. So Y is equal to, we are going to get, if input is equal to, if Y is equal to 0 means Y is equal to 1. If input is equal to 1 means output is equal to 0, because if A is equal to 0 means this is open. Whenever the switch is open, then whatever this voltage is same waves across this voltage. So Y is also equal to, means is equal to 1. If suppose A is equal to 1 means it is short circuit. So voltage drop across this is equal to 0. So you are going to get this as 0. So simply we can say complement of each other. If A is equal to 0, Y is equal to 1. If A is equal to 1, Y is equal to 0. If A is equal to 0 means this is open. So Y is equal to 1. If A is equal to 1 means this is short circuit. So Y is equal to 0. So this is the concept that we always have to understand. So whenever the plus VCC means 1, 0 means 0. So plus VCC means high voltage is nothing but 1, logic 1. Low voltage means logic 0. So we are always going to use the positive logic. So this is the concept that we always have to understand. So in a NOT gate, this is called as the symbol, or you can say symbol, and this is the truth table, and this is the circuit diagram. Let me discuss about the AND gate. Second basic gate is called as the AND gate. So this is the symbol of a AND gate. So let me take, there are two inputs A and B, and this is the output Y. So Y is equal to A dot B, or simply we can say A into B or A dot B, it is same, or A and B. You can call it in any other fashion. So always A into B is always equal to B into A. See, either you interchange the input terminals, still you are going to get the same output. Even if you interchange the input terminals, we are going to get the same output. Even if you interchange the input terminals, we are going to get the same output. So Y is equal to AB, so A into B is always equal to B into A. Suppose A into B dot C is always equal to A dot B dot C. Simply it indicates that suppose A and B, if you are going to give input to one, with two input, or we can say basically A into B is called as the, there is one AND gate with two inputs, and if you give again to C, then still the same as A dot B into C. You can see clearly A dot B dot C is always equal to A dot B dot C. So this is called the commutative property, and this is called as the associative property. So commutative property is satisfied by the AND gate, and the associative property is also satisfied by the AND gate. So both the commutative property and the associative property is being satisfied by the AND gate. So A dot B of dot C is equal to A dot of B dot C. So this is called the commutative property, and this is called as the associative property. So now let me draw a truth table for this AND gate. Inputs are two inputs A, B, and output is Y. Y is equal to A dot B. And when you told you, whenever 0, 0, you are going to get 0. 0, 1 means 0. 1, 0 means 0. 1, 1 means 1. So this is basically for AND gate. Suppose if I want to draw a circuit diagram, so this is the circuit diagram for the AND gate. So you can see clearly, this is the plus VCC. So this is a resistor. So we are going to keep the two diodes like this. So this is the A and this is the A and this is the output line. Suppose if A is equal to 0 and B is equal to 0, means these two diodes are on because this anode potential is greater than cathode potential. So both the diodes are on. So we are going to get 0 voltage now. So 0 we are going to get. Suppose A is equal to 0 and B is equal to 1, means this is open and this is on. So we are going to get short circuit. So we are going to get 0. Similarly, if A is equal to 1 and B is equal to 0, means this is open circuit and this is short circuit. So we are going to get short circuit and the output is equal to 0. Similarly, if we are going to use 1 so 1 is I already told you, if both are having the same potential across the diode, it is unbiased, means we are going to assume as an open switch. If both the P junction and N junction have the same voltage, then we are going to assume it is basically, simply we can assume that unbiased means open circuit. So therefore, again both are open. Whenever both are open, whatever the input voltage is here, so we are going to get plus P series 1. So this is a concept that we always have to understand. So therefore 0 0 is 0, 0 1 is 0, 1 0 is 0, 1 1 is 1. So this is the circuit diagram of a AND gate. So whenever I already told you for a diode, if the P voltage is greater than N voltage, which is the forward bias means which is the short circuit. For a diode, if the N, we can say if the cathode is greater than anode potential, it is a reverse bias means open circuit. If suppose both the P and N junction, cathode and the anode and cathode junction have the same potential, it is called unbiased. So we are going to assume it as an open circuit. Same procedure we have to use here also to analyze this circuit. So we are going to get the output expression as A into B. So this is the circuit that is going to present in this symbol. Now let me discuss about the OR gate. So this is basically the symbol of a OR gate. You can see inputs are A and B and is Y is equal to A plus B. So now if I want to know about the truth table, which is A and B, Y is equal to A or B. See 0 0 means 0, 0 1 means 1, 1 0 means 1, 1 1 means 1. So this is the truth table for this two input OR gate. If I want to draw the circuit diagram, so we have to draw the circuit diagram in this fashion. We can see clearly this is A and B, the two dots in this fashion, and this is the resistor. So we are going to find the voltage across this resistor, which is Y. Y is equal to A or B, we are going to get. Suppose you can check easily. If both are 0, means here also 0, here also 0, so both are open circuit. So both lights are open circuit means unbiased. So we are going to get a voltage of 0 because the short circuit. So current is equal to 0 in the circuit, so it is 0. If suppose A is equal to 0 and B is equal to 1, A is equal to 0 and B is equal to 1. If B is equal to 1, then it is going to become short circuit. So therefore whatever this B, same as the Y, so Y is equal to 1. If suppose A is equal to 1 means this diode is going to get on, so whatever the Y, same B we are going to get here, which is on. If both are on, then these diodes are basically short circuit, so we are going to get Y is equal to 1. So this is the circuit diagram of a OR gate. So this is the circuit diagram of a OR gate. So you can see clearly here this is the circuit diagram of a OR gate. So now here A plus B is always equal to B plus A. Even if we interchange the inputs, same result we are going to get. So therefore A plus B is equal to B plus A. So A plus B is always equal to B plus A. So we can say even if we interchange the inputs, same thing that we are going to get. So therefore this is called as the OR gate. So this is called as the basically OR gate. So now here suppose A plus B whole plus C is equal to A plus bracket of B plus C. This is called as associative property. Even this is also true. So we can say basically the OR gate is going to satisfy both the commutative property and also the associative property. So both the commutative property and also associative property is being satisfied by the OR gate. So this is the symbol, this is the circuit diagram, this is the properties which is satisfied by the OR gate, and this is the truth table. Now one more gate we are going to discuss is called the NAND gate. So NAND gate is basically, this is the AND gate. So if you keep a dot, if you keep something at the input, it is basically so combination of both AND gate and also NOT gate. So NAND gate is the combination of both AND gate and the NOT gate. So this is the basic representation of the NAND gate. If the inputs are A and B, output is equal to A into B whole bar. So this is called as the expression of the output. So now if you want to see clearly, if I want to try the truth table, then we are going to get AB pi is equal to A into B whole bar. For 0 0 we are going to get 1, and for 0 1 we are going to get, because for 0 0 A into B is equal to 0 with complement is equal to 1, and for 0 into 1 A into B is equal to 0 with complement is equal to 1. For 1 into 0 A into B is equal to 0 1 complement is equal to 1, and for 1 into 1 A into B is equal to 1 1 complement is equal to 0. So this is the output expression that we are going to get for a NAND gate. For NAND gate we are going to get the expression in this format. So now if I want to draw a circuit diagram, then this is the circuit diagram for a NAND gate. So this is the circuit diagram for a NAND gate. So you can see clearly these are the two transistors. Two transistors we are going to keep in this format, and the inputs of these transistors are A and B. So this is the place VCC and this is the resistor. So this is called as Y is equal to A into B whole bar. So what I told you, these two switches are in series. These two switches are in series, but they are parallel with respect to bulb here. So we have to assume the bulb is here, and we have to assume this parallel with respect to bulb. So what is the A? Y is equal to A into B whole bar. So these are the two switches in series. And basically if you keep a bulb here, it is in parallel with respect to these switches. So Y is equal to A into B whole bar. So this is the expression that we are going to get here. Suppose if A is equal to 0, B is equal to 0, both are open. So Y is equal to 1. If A is equal to 0, B is equal to 1. This is open and this is on. And your current in switch is equal to 0. So Y is going to get on. So therefore Y is equal to 1. If A is equal to 1 and B is equal to 0, again this switch is on and this is off. And then again same thing we are going to get this plus VC means Y is equal to 1. If both are on, then only overall we are going to get short circuit, then Y is equal to 0. So this is the circuit diagram of a NAND gate. So now here, suppose now I want to see A into B whole bar is always equal to B into A whole bar. Even if we change the terminals of A and B, same thing that we are going to get. So it is going to satisfy the commutative property. So it is going to satisfy the commutative property. And now we will see what is going to happen. See, suppose A into B whole bar dot C whole bar is not equal to AC bar dot B whole bar. This is called the associative property is not satisfied. So associative property is not satisfied by the NAND gate. This is basically NAND gate associative property which is not satisfied. So only commutative property is satisfied by NAND gate, but not the associative property. So only the commutative property is being satisfied by the NAND gate, but not the associative property. So this is the symbol, this is the truth table, and this is the circuit diagram. So now we discuss about the NOR gate. So this is basically NOR gate symbol. So like this is basically a combination of OR gate and the NOT gate. So combination of both OR gate and the NOT gate is called as the NOR gate. Input is A and B, and this is Y is equal to A or B whole complement. Y or B, A or B whole complement. So now I want to draw the truth table. Then A into B, Y. So A, B, Y, 0, 0, 1. So 0, 0, 1 and 0, 1, because here 1 or 0, 0, A or B is equal to 0, whole complement is equal to 1. And 0 or 1 means A or B is equal to 1, 1 complement is equal to 0. And 1 or 0 means 1, and whole complement is equal to 0. And 1 or 1 means 1. 1 whole complement is equal to 0. So this is the, we can say the output expression that we are going to get here for this NOR gate. So now if I want to draw a circuit diagram, so you are going to get the circuit diagram in this format. So you can see clearly the two switches are now in parallel. They are in parallel means A or B. Again it is parallel with respect to bulb. So therefore again you have to do the complement here because they are parallel means A or B. Again they are parallel with respect to bulb means we have to do again the complement. So therefore A or B will complement. So you can see clearly, suppose if A is equal to 0, B is equal to 0. So this is off, this is off, this is off. So Y is equal to 1. If suppose A is equal to 0 and B is equal to 1, means this is off and this is on, then we are going to get Y is equal to 0. If this is on and this is 0, means if this is on and this is off means, and again you are going to get short circuit means Y is equal to 0. If both are on means both are short circuit. Both the short circuit, so therefore Y is equal to 0. So this is the, we can answer the circuit diagram we are going to get for this NOR gate. So now A or B whole bar is always equal to B or A whole bar. Means even if you interchange the A and B, you are going to get the same output. So the commutative property has been satisfied. The commutative property has been satisfied. Now we'll see the associative property. So ARB whole complement, ARB whole complement bar C whole complement is not equal to ARC complement plus B whole bar. So we can say that the associative property is not satisfied. The associative property is not satisfied by the NOR gate. So associative property is not satisfied by the NOR gate. Only the commutative property has been satisfied by the NOR gate. So now we are going to discuss about the XOR gate, or it is also called as the XOR of XOR gate. In the name is same. XOR gate is also called as the XOR gate. So this is a symbol. This is a symbol for a XOR gate. So like this is a symbol. So you can see clearly this is a symbol of a XOR gate. Inputs are A and B, and output Y is equal to A XOR B. So basically here A, B and this is the Y. Two tables I want to see here. So I already told you. Whenever the number of input ones are, so suppose for given input, if the number of input ones are odd, then only you are going to get is output as 1, otherwise you are going to get 0. Listen carefully, if the number of inputs having a 1, the logic one has odd number, then you are going to get the output as 1, otherwise you are going to get 0 in the remaining cases. So you can see clearly for 0, 0, the number of inputs ones are 0, so therefore you are going to get output as 0. Whereas for 0, 1, the number of input ones are 1 odd number, so you are going to get 1. If 1, 0 means the number of input ones are 1, it's odd number, so you are going to get output as 1. The number of input ones are here 2, so it's even number, so output you are going to get 0. So listen carefully, whenever for XOR gate or XOR gate, if the input number of logic ones are odd number, then only the output is 1, otherwise it is always 0. So always A XOR B is always equal to B XOR A, means the commutative property is being satisfied. So A XOR B means if you interchange A and B, still the result is same. So A XOR B is always equal to B XOR A. Now A XOR of B XOR of C is equal to A XOR of B XOR of C is equal to A XOR of B XOR of C is equal to A XOR of B XOR C. So you can see clearly the associative property is being satisfied. The associative property is being satisfied. See, A XOR B XOR of C is equal to A XOR of B XOR C. So this is associative property. Yes, the commutative property is satisfied and the associative property is also satisfied. Only the associative property is not satisfied only in the NAND gate and the NOR gate, but here it is satisfied. So A XOR B XOR C is equal to A XOR of B XOR of C is equal to A XOR of B XOR C. It is also equal to A XOR of C XOR of C, means you can do XOR in any manner. We can do any manner. You can do any, if you want A XOR of B XOR of C, you can do in any fashion, we are going to get the same result. So A XOR of B XOR of C is equal to A XOR of B XOR of C is equal to A XOR of B XOR of C, or A XOR of C or XOR of B. Means you can do in any fashion, still you are going to get the same result for the XOR. So you can say both the associative and the commutative, both the commutative and the associative properties being satisfied by the XOR gate. Suppose you can see clearly, if one of the input is A and the other input is 0, then what is going to happen? If A is equal to 1, then 1, 0 is nothing but 1. If A is equal to 0, so 0, 0 is again equal to 0. So therefore, listen carefully, if A is equal to 1, 1, 0 is nothing but 1. If A is equal to 0, 0, 0 you are going to get 0. So whatever the input A, same thing that we are going to get. So this is called as the output is also equal to A. If A is equal to 1, here also output is equal to 1. If A is equal to 0, here also output is equal to 0. So therefore, here we can say that if one of the input is A and the other input is 0, then always the output is always equal to A for this XOR gate. See, I already told you A XOR B is equal to A bar B plus A B bar. A XOR B is equal to A bar B plus A B bar. So suppose for XOR gate, if one of the input is A and the other input is 1, then what is going to happen? Suppose if A is equal to 0, then output is equal to 1. If A is equal to 1, the output is equal to 0. So it is a complement of input. So if the input is A, the output is equal to A bar. So this is the point that you always have to keep in your mind. So 0 means same thing you are going to get. If 1 means it is a complement of the input. So if number of inputs are odd, then output is 1. Then only output is 1. And all it will in the XOR gate, if the number of input ones are odd, then only you are going to get output as 1. Otherwise you are going to get the output as 0. If number of input ones are odd, then only output you are going to get as 1. Otherwise in all the cases we are going to get as a 0. If the number of input ones are odd, then only the output is 1. Otherwise you are going to get as 0. See, A XOR of A. I have already told you A XOR of A is nothing but simply if you do the expansion of this one, see 0, suppose if A is 0 means 0 plus 0 XOR 0 is equal to 0, 1 XOR 1 is also equal to 0. So we are going to get A XOR of XOR is always equal to 0. Suppose A XOR of A bar is always equal to 1 and already told you if A is equal to 0, 0 XOR 1 is equal to 1 and 1 XOR 0 is equal to 1, so it is always equal to 1. Similarly, A XOR of 0, just now we have seen A XOR 0 is equal to A and A XOR of 1 is equal to A bar. Just now we have seen. So these are the four things that we always have to keep in your mind. So A XOR A is always equal to 0 and A XOR A bar is always equal to 1 and A XOR 0 is equal to A and A XOR of 1 is always equal to A bar. So this is the very important results of the XOR. So suppose there are n variables. So there are n variables. I have already told you for n variables you are going to get 2 to the power of n combinations. So out of this 2 to the power of n combinations, then 2 to the power of n minus 1 min terms or 2 to the power of n minus 1 max terms, maximum only these two number of things can be present. So half of this one. So 2 to the power of n is number of combinations. So half of that can be only means 2 to the power of n by 2 is nothing but 2 to the power of n minus 1. So only 2 to the power of n minus 1 number of min terms are the 2 to the power of n minus 1 max terms relating to this XOR. Basically it is in terms of XOR. I am speaking only in terms of XOR. Only in terms of XOR means min terms means the output are equal to 1 and the max term means the output is equal to 0. So these may number of min terms and max terms. These may number of min terms you are going to get 1 and this may number of max terms you are going to get as 0. So this is the concept which is only for this XOR. Only for this XOR I am speaking. So therefore for n variables you are going to get 2 to the power of n combinations. Out of this 2 to the power of n combinations, 2 to the power of n by 2 means half of that will be min terms and half of that will be maximum. So 2 to the power of n by 2 is nothing but 2 to the power of n minus 1 number of min terms, which means the corresponding output is equal to 1 that we are going to get. And 2 to the power of n minus 1 max terms means the corresponding output is equal to 0, you are going to get half of that, half of 2 to the power of n. So now the last gate is called as the XNOR gate. So this is the XNOR gate, means if you keep a NOR gate for the XOR, you are going to get the XNOR. So for XOR, if you keep a NOR gate, you are going to get this as called as the XNOR. So this is basically XNOR. So this is A, this is B. So Y is equal to A XNOR B. This is the unit measure like dot the circle. Dot the circle is called as the A XNOR B, means A XOR B whole complement. So now we can see this is the truth table AB, Y is equal to X not B. I already told you is the complement of the previous one. So 0, 0, in the previous case it is 0, means you are going to get here now 1. Here 0, 1, in the previous case it is 1, so now it is, you are going to get 0. For 1, 0, in the previous case we are going to get 1, means now it is 0. For 1, 1, in the previous case we are going to get 0, but now we are going to get 1. So this is the concept that you always have to understand. This is complement of the previous case. So now you can see clearly here A XOR B. See A XOR B, or you can say A XOR B is always equal to B XOR A. I already told you A XOR B is equal to AB plus A bar B bar. So here even if you interchange the inputs, you are going to get the same result. So you are going to get the same result. So A XOR B is always equal to B XOR A. So So commutative property is satisfied. So now A XNOR of B XNOR of C is not equal to A XNOR of B XNOR C and A XNOR of C XNOR C or XNOR of B. So we can say that here simply this is the for odd inputs. So like this it is not possible. Only for even inputs it is possible. So A XNOR of B XNOR of C XNOR of D is equal to A XNOR of B XNOR of C XNOR of D, or simply A XNOR of B XNOR of C XNOR of D, which you can do in any fashion. We are going to get the result. This is only for even inputs, but this is not for odd inputs. Odd inputs you should not do like this. Odd inputs you should not do like this. For even inputs you can do in any fashion. See, either you can take first two and the last two, and overall you can do the XNOR, or simply take the first two, then this one and this one. So you can go for any fashion. We are going to get the result for even inputs, but not for the odd inputs. So for odd inputs you should not do like this. For odd inputs you should not do separate like this. Separately you should not take here. Separately you should not do this like this. But for even case you can do in any fashion separately, you are going to get the same result. So this is what I am trying to tell you. So for odd inputs you should not do separately like this. Whereas for even inputs you can take in any separate fashion, you are going to get the same result. So listen carefully. Evaluate A XOR B XOR. See, A XOR B XOR of C is nothing but A XOR of B XOR of C complement. So now we can write like this. I already told you this A XOR of B XOR of C is nothing but we can write like this, which is here A XOR of B XOR of C is equal to A XOR of C XOR of B is equal to A XOR of B XOR of C. So like this you can do in any fashion. We are going to get this result. So A XOR of B XOR of C is equal to A XOR of B XOR of C one complement is equal to A XOR of B XOR of C, which you can do in any fashion in A XOR of C XOR of B or A XOR of B XOR of C. So you are going to get the same result. So this is one of the important point, very important expression. So this is a condition here. This is always a condition. So we can say clearly this is the very important condition. Only for our inputs it is not possible. Only for even inputs it is possible. So now A XNOR A is always equal to 1 here, and A XNOR A bar is always equal to 0 here, and A XNOR 0 is always equal to A bar, and A XNOR of 1 is always equal to A. Suppose if one of the input is 0, and if you are going to give A, then definitely I already told you, then A XNOR of 0 is always equal to A XNOR of 0 is always equal to A bar. So you are going to get here A bar. And here, if one of the input is 1 and this is A, so A XNOR of 1. So what is the A XNOR of 1 is always equal to A. So you are going to get A. In the previous case it is A and it is A bar, but now it is the reverse of the previous case. It is now A bar and A. So this is the point that you always have to understand. In the previous case it is A and it is A bar. Now it's a complement. It is A bar and A reverse fashion. So this is the concept that you always have to understand in this one. So therefore, this is basically XNOR symbol, this is the truth table, and this is the commutative property satisfied. But associative property is based on conditions. For some cases it is satisfied, but for some cases it is not satisfied. And also, this is the, see, only for our inputs you can't take it like separately, but for other inputs you can take separately and you are going to get the same result. So these are the important formulas of different types of gates. So now we have discussed the different types of gates. The basic gates are basically called as the AND gate, and the NOT gate. NOT gate, AND gate and OR gate are called the basic gates, and the universal gates are the NAND and the NOR are said to be universal gates. So we will discuss something more about this one. Now we are going to discuss the other concept which is called the NAND gate as universal logic gate. And what I told you, AND gate, OR gate. See, NOT gate, AND gate and the OR gate are called as the basic gates. So now, whereas the NAND gate and NOR gate are called as the universal gates. So now discuss why these are called as the universal gates. Because these NAND gates and NOR gates, NAND and NOR gate, with the help of this individual, we can build any of the gate. So just by using NAND gate, we can build all the gates, or just by using the NOR gate, we can build all the gates. That is the reason we can say NAND gate and the NOR gate are called as universal gates, which means with the help of that gate, only with the help of these gates, you can build any of the gate that you want. So that is the reason these are called as the universal gates. So now you can see clearly NAND gate as a universal logic gate. So NAND gate has a universal logic gate. So this is the NOT. So how to represent the NOT gate in terms of NAND? Just see whatever this NAND gate, just do the means just tie these two terminals to a common terminal of A. So then what is the complement? Y is equal to both are same. So A into A, all complement is nothing but A into A is equal to A. So A bar. So we are going to get this is called as the, so output is equal to A bar. So this is called as the NOT gate. So with the help of NAND gate, if you join these two into terminals to a common input of A, it is called as the NOT gate because it is going to output is equal to A bar, because A into A whole complement is equal to A into A is equal to A complement is equal to A. Similarly, for AND gate, I already told you, for if you want to represent the AND gate in terms of NAND gate, just I already told you just to the complement of here, because I already told you the NAND gate is a combination of AND and NOT. So if you want to remove this NOT, just keep here another NOT gate, or simply we can say in terms of NAND gate it is like this. So we can say this is called as the A into B, because here AB, A is equal to AB over bar, again complement is equal to AB. So we require two NAND gates. We require two NAND gates to represent the AND gate, and we require one NAND gate to represent the NOT gate. Similarly for OR, suppose if we want to build the OR gate, with the help of NAND gates, we need three gates. Three NAND gates you will require. So like this, here A is A bar, here B means here B bar. So A bar plus A bar into B bar whole bar is nothing but A plus B. So A bar into B bar whole bar is equal to A plus B. It is nothing but Y is equal to A plus B is nothing but there is a OR gate. So we need three NAND gates to represent a OR gate in this combination. So for NOR gate, for NOR gate, I already told you, for whatever the OR gate, just keep a, we can say just keep another NOR gate. So this is basically same as the previous one. This is OR gate. So now you have to keep a NOR gate, means in terms of NAND gate you have to keep another NAND gate. Then you are going to get this is called as the NOR gate. Up to here just A or B, again complement is A or B whole complement. So this is called as the NOR gate. So we require four number of NAND gates to make a NOR gate. If suppose it is called as the XOR gate. XOR gate means simply here I already told you XOR is equal to A XOR B. Then how to represent the XOR gate in terms of NAND gate is very simple. Here is the NOT gate. This is basically NAND gate, and here you have to take like this, and here it is a NAND gate, here it is a NAND gate, and here you have to join together. So this is called as the overall A XOR B. Simply we can say, if you do the simplification of all these things, finally you are going to get the same result, which is A XOR B. So like this you have to build this one. Suppose now for XNOR gate, how to build the XNOR gate? Just for the previous one, you have to keep a NOT gate here. NOT gate means here, in terms of NOT gate, you have to keep another here. So therefore, this is called as the basically XNOR gate. This is the XNOR gate. So finally, we can say there are total 1, 2, 3, 4, 5. 5 number of NAND gates are required to make a XNOR gate. So this is the NOT gate, this is the AND gate, and this is the OR gate, and this is the NOR gate, and this is the XOR gate, and this is the XNOR gate. So totally 1 NAND gate is required to make a NOT gate, 2 NAND gates are required to make the AND gate, 3 NAND gates are required to make the OR gate, and 4 NAND gates are required to make the NOR gate, and 4 NAND gates are required to make the XOR gate, and 5 NAND gates are required to make the XNOR gate. So this is the circuits that you always have to keep in your mind. So now you see NOR gate as the universal logic gate. I already told you NOR gate is also called as the universal logic gate. So with the help of NOR gate, how we are going to represent the different types of gates we are going to see here. So basically this is the NOR gate. So NOR gate means I already told you, just you have to make these two things combine together. This basically A XOR means A or A whole bar is nothing but AR is nothing but A bar is nothing but A bar, so you are going to get A bar. So if you join these two input terminals to a common input of the A, it is called as the NOT gate. So this is the way that you have to do the NOT gate in order to make the NOT gate. So OR gate means here, and already told this is this is called the NOT gate. So another NOT we have to keep here. So to get the overall OR gate means in terms of NOT means in terms of this circuit we have to keep here to get this one. So this is ARB one complement and here is I1 complement is equal to ARP. See for AND gate, if you want to make the AND gate, so this is the way that you have to do this one. See this is A, this is B, here is A bar, B bar. So A bar plus B bar whole bar is equal to A into B. So this is the way that you have to do the connection of NOR gates to make the AND gate. Similarly for NAND gate means this is the AND gate, another NOT gate we have to keep here. So if NOT means in terms of here, this circuit we have to keep here. At here we have to keep this circuit. So we are going to get this one. So this is the circuit of the NAND gate in terms of the NOT gates. See now XOR. XOR means you can see clearly this is the circuit diagram we are going to get. So this is the circuit diagram we are going to get for the XOR gate. If you want XOR, just remove this one. Just remove this one. We are going to get this one. So this is called as the XOR gate. So this is circuit diagram that you always have to understand. So therefore, one NOT gate is made the NOT gate. Two NOT gates are required to make the OR gate. 3 NOR gates are required to make the AND gate, and 4 NOR gates are required to make the NAND gate. 5 NOR gates are required to make the XOR gate, and 4 NOR gates are required to make the XNOR gate. So these are the two things, these two graphs, you can say this OR gate and NAND gate, the circuit diagrams for each and every gate that you always have to keep in your mind. So now I am going to give a summary of all the things that we have learned. See, for logic gates, the different types of logic gates, the minimum number of NAND gates required, the minimum number of NOT gates required. For NOT gate, we require one NAND gate, and here we require one NAND gate, and also to do the NOT gate, we require one NOT gate and one NOR gate. Similarly, for AND gate, we require 2 NAND gates and 3 NOR gates. To implement OR gate, we require 3 NAND gates and 2 NOR gates. And for XOR, we require 4 NAND gates and 5 NAND gates. 4 NAND gates and 5 NOR gates. To build the XNOR gate, we require 5 NAND gates and 4 NOR gates. To build the NOR gate, we require 4 NAND gates and 1 NOR gate. For NAND gate, we require 1 NAND gate and 4 NOR gates. For A bar plus B, we require 2 NAND gates to represent this one, whereas here 3 NOR gates to represent this one. So for A bar B, we require 3 NAND gates to build this circuit, and we require 2 NOR gates to build this one. Similarly for half adder, we require 5 number of NAND gates to build the half adder, whereas 5 number of NOR gates are required to build the half adder. For half subtractor, we need 5 number of NAND gates to build the half subtractor, and 5 number of NOR gates are required to build the half subtractor. Similarly for full adder, we require 9 number of NAND gates are required to build the full adder, and 9 number of NOR gates are required to build the full adder. Similarly for full subtractor, we require 9 number of NAND gates are required to build the full subtractor, and 9 number of NOR gates are required to build the full subtractor. So this is the table that you always have to keep in your mind. So all these gates, this number of NAND gates are required, and this number of NOR gates alone. So only NAND gates alone required to build all these things, and only alone NOR gates are required to build this one. So this is the concept that you always have to keep in your mind. So now we are going to discuss about the bistable and the astable multivibrator. So bistable and the astable multivibrator. So bistable means basically we are going to have 2 stable states. And astable means the output is going to change continuously. That is the meaning of the bistable and the astable multivibrator. So bistable means we are going to have the 2 stable states, and astable means we are going to change the output continuously from 0 to 1 and 1 to 0 continuously. So there is not even one state as the astable. So because of this reason, we are going to call this as the astable multivibrator. So now we are going to learn these two important concepts. So you can see clearly here, these are called as the NOT gates. So this is the one gate, NOT gate, second NOT gate, third NOT. So third NOT gate, like there are n NOT gates. So then I am going to give the feedback from the output to the input in this manner. So I am going to keep n number of, we can say I am going to keep n number of NOT gates, and I am going to keep a feedback from output to the input. So listen carefully. When number of inverters inside the feedback are even, then it is called as the bistable multivibrator. Suppose if the number of inverters, are NOT gates, you can call anything. So when the number of inverters or the NOT gates inside the feedback are given, then it is called as the bistable multivibrator. So we can say clearly, if suppose even number of inverters and the NOT gates present between the feedback, then we are going to call this as the bistable multivibrator. Suppose the number of inverters inside the feedback are odd, then it is called as the astable multivibrator, or square wave generator, or clock generator, or ring oscillator. So we can say when the number of inverters inside the feedback are odd, then it is called as the astable multivibrator, or square wave generator, or clock generator, or ring oscillator. So suppose if the number of NOT gates or the inverters between the feedback are odd number, then we can call this as basically astable multivibrator, or square wave generator, or clock generator, or ring oscillator. Means so I already told you the output is always going to change from 1 to 0 and 0 to 1 continuously. So not even one state is stable for all the time. So because of this reason only, it is called as the astable multivibrator, or square wave generator, or clock generator, or ring oscillator. Then if you want to find what is the overall time period, the overall time period is equal to T into N into TPD. So total time period is equal to T into N into TPD. N is called as the number of inverter inside the feedback. So I already told you it should be always an odd number. So N is called as the number of inverters which are inside the feedback, and N is always an odd number, and TPD is called as the propagation delay of the inverter. So TPD is called as the propagation delay of each inverter. So this is the overall time period that we are going to get, which is T is equal to 2N into TPD. Where N is the number of inverters present inside the feedback, and it is always an odd number, and TPD is called as the propagation delay of the inverter. So finally I can say that whenever the inverters inside the feedback are even in number, so it is called as a bistable multivibrator, means always you are going to get two stable states for all the time. So because of this reason only, it is called as the bistable multivibrator. Suppose if the number of inverters inside the feedback are odd, then we are going to get the output continuous variation from 1 to 0 and 0 to 1. So not even one state is stable, so it is called as the astable multivibrator, or square wave generator, or clock generator, or ring oscillator. And if you want to find what is the time period in this astable multivibrator, the total time period is equal to 2 into 8 into TPD, where N is called as the number of inverters present inside the feedback, and it is always an odd number, whereas TPD is called as the propagation delay of the inverter. basically let me tell you which are regarding the stable multivibrator and the unstable multivibrator. So you can see clearly in this picture, I have taken two inverters, or we can say two NOT gates between the feedback. So whenever the number of inverters inside the feedback is even, it is said to be bistable. So let me explain. Suppose if the input is 0, here it is output is not get much 0, side is 1, one side is 0. So same thing you take 0, 1, 0. So this is going back to here. So it is going back to the input. Again 0 is 1, 0. You can see clearly the output is always stable state of 0 for all the time. Suppose if the input is 0, here it is 1, it is 0. Again same thing is repeating. So always we are going to get the output as 0 for all the time. So we can say this is one of the stable state. Suppose if I give input as 1 here, then what is going to happen? Here it will be 0, here it will be 1. Again 1 comes here, again 0, again 0. So here 1 will be always for all the time. So I am showing this here. If input is 1, here 0, again 1, again 1 came here, again 0, again 1. So for all the time we are going to get a stable state of 1 also. So here if you give input as 0, the output is always 0 for all the time. If you give input as 1, output is always 1 for all the time. So because of this reason only, there are two stable states you can see, 0 stable state and 1 stable state. So total there are two stable states. So because of this reason only, it is called as the bistable multivibrator. Suppose if the number of inverters inside the feedback are odd integer, then it is said to be a stable multivibrator. So for example, I have taken my inverter or NOT gate between the input and the output. So there is a feedback present from output to input. Suppose if the input is 0, output is 1, this output is came back to the input, again it will become 0, this output is came back to input by feedback, again the output is 1, again this one is came back to the input, again the output is 0. You can see the output is always varying from 1, 0, 1, 0 continuously. So
క్లాస్ చెప్తాను అత్తమ్మ అత్తమ్మ
So you can see clearly the output is changing from 1 to 0, 1 to 0 continuously. So we can say not even one state is stable. So because of this reason it is said to be a stable multivibrator. So here we have two stable states 0 and 1. So it is called as a bistable state, bistable multivibrator. But here there is not even one stable state. So because of this reason it is called as the unstable multivibrator. And here time period is nothing but here time period is equal to 2, t is equal to n into t today. This time period is only for unstable but not for the stable bistable multivibrator. So this is a concept that you always have to keep in your mind. So now we discuss about the other concept which is called as the number systems. So basically the number systems that we are going to discuss in the, we can say in this digital electronics are the, we can say binary system, octal system, decimal system, hexadecimal system and randomly any other decimal system. So we can say some number systems. So radix means the number of digits which are used in that system. So whatever the system that we are going to choose, the number of digits which are used in this called as a radix, or we can also call it as the basic or radix. Radix means basically you can say the number of digits that we are going to choose in that system, in that number system. So radix means we are going to represent by a symbol R. So it is going to tell you the number of digits that we are going to choose in that number system. And here the numbers used in the system. So numbers used in that system we are going to discuss here. So see clearly, now we are going to study about the binary number system. Binary number system has the radix which is 2. We means we are going to use two digits there, which is 0 and 1. Only these two digits that we are going to choose here. Now comes the octal number system. For octal number system, the radix is 8. So we are going to choose 8 digits like 0, 1, 2, 3, 4, 5, 6 and 7. Then comes the decimal number system. Decimal number system has a radix of 10. Means 10 digits that we are going to choose from 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Then comes the hexadecimal number system. For hexadecimal number system, we are going to choose the radix as 16. Means 16 digits we are going to choose in that number system starting from 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then comes A, B, C, D, E and F. A is called as the 10, B is called as the 11, C is called as the 12, D is called as 13, E is equal to 14 and F is equal to 15. Then comes any other general number system. Let me assume some general number system has a radix of R, means we are going to use the R number of digits starting from 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A up to R minus 1. So if you see clearly, the maximum number in that number system is always 1 lesser than the radix. So you can see clearly the maximum number which is used in the decimal system is always one number lesser than its radix. Here, which is the radix number is 2, so 2 minus 1 is 1, so 1 is the maximum number. The radix is 8, 8 minus 1 is 7, so maximum number is 7 here. And here the radix is 10, so 10 minus 1 is 9, so this is the maximum number used here. And for 16, radix is equal to 16, 16 minus 1 is equal to 15, which is F is equal to 15. And for radix R, the maximum number is R minus 1, so R minus 1. So finally we can say that in a particular number system of radix R, the maximum number that we are going to choose is 1 lesser than the radix. So total digits that we are going to choose in the number system is equal to radix number. So for binary system, the radix is equal to 2, and the numbers which are used in the system are 0 and 1. And for octal number system, the radix is 8. So we are going to choose the number from 0, 1, 2, 3, 4, 5, 6 and 7. And for decimal number system, the radix is 10. So we have the numbers which are used in the system are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. And then comes the hexadecimal number system. So for the hexadecimal number system, the radix is 16. So therefore, we are going to choose the number from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And for general any other number system of radix R, so we are going to choose the number from the numbers which are used in the system are basically 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C up to R minus 1. So this is a concept that you always have to keep in your mind. Where A is equal to 10, B is equal to 11, C is equal to 12, D is equal to 13, E is equal to 14 and F is equal to 15. So now let me tell you about the decimal to any base conversion. So decimal to any base conversion. Suppose the question they have given me a decimal number system. Then I want to convert into any other base system, any other general base system, any base if I want to convert. Then what is the procedure? It's very simple. Let me assume this is a decimal number system. For decimal number system, the radix is 10. So we are going to choose like bracket in base 10 means whatever the number present in this bracket is basically number belongs to decimal number system, the radix of 10. So suppose there is a number like this, there is a dot here, x1, x2, y1, y2. So this is basically called as the integer part and this is called as the fraction part. So this is called as the integer part and this is called as the fraction part. So now I will tell you how to convert a decimal number system to any other base system. The simple procedure is first you have to take the integer. So first you have to take the integer. So I want to convert this basically into any other base system of radix R. So any other base system as a radix of R. So how to do this one? So keep the decimal here. So now here whatever the integer you take here and divide with the base of this number system. So whatever the base that you have, this number system that you want to convert to certain base system. So these values you have to take here and you have to divide this integer part. So if you do this, if you divide this integer part, so here you are going to get the remainders. So here you are going to get all the remainders. So here you are going to get all the remainders. Then you have to collect all these remainders. You have to collect all these remainders in this fashion. So you have to collect all the remainders in this fashion. These are quotient values and these are the remaining values. So you have to collect only the remainder values in this procedure and you have to keep in this arrow. So whatever the number coming here, it will be first, and whatever the number coming here, it is a last. So in this fashion you have to collect all these numbers and you have to keep in this sequence before the part. So now you have to take the fraction part. So you have to take the fraction part which is 0 point, the fraction part you have to take here. And now for the fraction part you have to multiply by this base r. With this radix r you are going to multiply. So then you are going to get basically, so you are going to get some number. So here always you have to again do this one, again you have to multiply, again you have to do multiplying until you get a one number, until you get any other single number. So you have to do things that continue this procedure until you get a single number, to any other single number, you have to continue this procedure until you get a single number, and you have to collect all these points. So before the dot, whatever the numbers are there, you have to collect all these values you have to collect. So if you collect all these values and if you keep in this way, if you collect all these values and if you keep in this way, so this is called as this is the way that we are going to convert the decimal number system to a base number system. And one more important point here is, suppose you got 1.11, then here, then if you take here, it will be always 0.11. This one value we have to take it. So only always it has to be 0.11. Suppose you got some 2.33, then 2 you have to consider. You don't have to consider here. Only you have to consider 0.33 into r. So all these values you have to collect and you have to keep here in this fashion. So like this arrow you have to keep until you have to repeat this process until you get a single number. A single number can be any value, either 1, either 2, or either 3, any value you are going to get. You have to repeat until this single value comes. So then finally this is the way that you are going to convert a decimal number system to a base number system. So finally I can say that whatever the integer part you have to divide and then you have to collect all the remaining values and you have to keep in this way. And whatever the fraction part you have to multiply by this r and you have to collect all these values and you have to keep it here. Then this is the way that you can convert from decimal number system to any other base conversion. So this is the principle that you always have to keep in your mind. Suppose if you want to convert any base system to decimal conversion, how to do this one? Suppose there is a number like this. So in this some base system of r, a number is given like this, which is x0, x1, x2, x minus 1, x minus 2. Then how to convert this into decimal number system, that we are going to see here. So whatever this radix of this base systems are, so here it is r to the power of 0, r to the power of 1, r to the power of 2, like this you have to continue up to here. Similarly here, r to the power of minus 1, r to the power of minus 2. So whatever the powers are there, you have to multiply with this corresponding values and you have to find it with the summation. Then you are going to get the resultant value in the decimal number system. So here r square into x2 plus r to the power of 1 into x1 plus r to the power of 0 into x0 plus r to the power of minus 1 into x of minus 1 plus r to the power of minus 2 into x of minus 2. So like this you have to do this one, and finally if you do a summation of all these things, then you are going to get a number in the format of decimal number system. So this is the principle that you always have to keep in the mind. So here, whatever the decimal number system, whatever the base number system they are given, first you have to keep r to the power of 0, r to the power of 1, r to the power of 2 in this manner, and here r to the power of minus 1, r to the power of minus 2, like this you have to continue here. And if you do a corresponding multiplication with respect to power and this values, which is x2 into r square plus x1 into r to the power of 1 plus x naught into r to the power of 0 plus x minus 1 into r to the power of minus 1 plus x minus 2 into r to the power of minus 2. So if you do the simplification, finally you are going to get a value in the terms of the decimal number system. So this is a way that we can convert any base system to a decimal conversion. So now we will discuss about the octal to binary conversion. So how to do the octal to binary conversion? Suppose in a question they are given an octal number and they want to convert into binary conversion. So how to do this one? See, each octal you get directly convert to 3-bit binary number. So if you want to convert the octal number to binary number system, very easy way. Whatever the octal number that you know, you have to convert into decimal. You have to convert into binary number by 3 corresponding digits. So for every octal number, there will be a 3-digit number, 3-digit binary representation. So replace that octal number by 3-bit binary number. The overall value that you are going to get is called as the, which is in the terms of the binary, we can say in the terms of the binary number system. So we can say each octal digit directly convert into 3-bit binary number. So if you convert each octal digit directly convert into 3-bit binary number, so this is the way that we can convert the octal number to binary conversion. So whatever the octal number is there, just convert into 3-bit binary number. Then 3-bit binary number. Then if you put all those values, it is called as the way of representing the binary number system of the corresponding octal number. So each octal digit directly convert to 3-bit binary number. Then this is a way that you are going to convert the octal number to binary number system. So each octal digit directly we are going to convert to 3-bit binary number, and the collection of all these things is called as the binary number. So each octal digit directly convert to 3-bit binary number. So this is the way that we are going to convert the octal number to binary conversion. Now the reverse process, which is binary to octal conversion. So if you want to do the binary to octal conversion, so this is a way. Suppose this is the binary number. So there is a dot here. So here in this arrow, you have to group the 3 digits. You have to group the 3 binary digits, and in this direction you have to group the corresponding 3 binary digits. So if you do like this, then for this grouping of 3 corresponding binary digits, then you have to figure out the corresponding octal number. Then this is called as the way to convert the binary number to octal conversion. So from this dot, from this direction, we have to group the 3 corresponding binary digits in this direction, and in this direction you have to group the 3 corresponding binary digits. If you do this process, then if you convert to correspond to a group of 3 bits of binary, if you convert to the octal, then all the values that you are going to get is basically octal conversion. So group 3 bits as shown in the direction. So therefore I already told you So whatever the dot is there, here group the 3 bits in this direction, here the group the 3 bits in this direction. So therefore, that grouping of 3 bits there, you are going to get a decimal number. You are going to get a decimal number or octal number. Then this is called as a basically an octal conversion, 1 to octal conversion. So grouping of 3 bits in the direction which is shown and convert to corresponding octal number. So whatever the number that we are going to get is basically an octal representation. So this is the way that we are going to do the binary to octal conversion. So now we discuss about the hexadecimal to binary conversion. So how to do a hexadecimal to binary conversion? See, convert each bit of hexadecimal digit to 4 bits of binary. That's it. So whatever the hexadecimal number is there, just convert the hexadecimal number to 4-digit binary number. And if you do for each and everything, then the overall value that you are going to get is basically a binary representation. So this is the way that you always have to do the hexadecimal to binary conversion. So convert each bit of hexadecimal digit to 4 bits of binary. So whatever the hexadecimal digits that we are going to see there, so for each and every hexadecimal digit represented by 4-digit binary number. The overall value that you are going to get is a binary conversion, which is hexadecimal to binary conversion. So convert each bit of hexadecimal digit to 4 bits of binary. So we are going to get a overall binary conversion. So now the reverse process, binary to hexadecimal. Suppose is the binary number, there is a dot here. So you have to group the 4 digits in this direction, you have to group the 4 digits in this direction. Then you can say that here, now replace this 4 bits binary, the 4 bit binary with the corresponding hexadecimal number. So we are going to get that. It's a way to convert the binary to hexadecimal. So group 4 bits as shown in the direction and group those 4 bits and convert that into hexadecimal. So you are going to get the binary to hexadecimal number. So group the 4 bits in the direction which is specified and convert that 4 bit binary to hexadecimal number. Then we are going to get a hexadecimal representation for binary. So the group 4 bits are shown in the direction. You are going to get the binary to hexadecimal representation. So now comes the hexadecimal to octal. See, I already told you hexadecimal to octal is very simple. Convert hexa to binary and then to octal. So if you want to convert hexadecimal to octal number, first thing is you have to convert the hexadecimal to binary and then go for binary to octal. And already told you hexadecimal to binary is nothing but, see, replace each and every hexadecimal number by 4 bit binary. Then you are going to get a binary representation. Now I already told you in the dot, I already told you how to group 3 bits and direction I already told you. So if you do that process and if you group the 3 bits in the directions and replace with the corresponding octal number, so you are going to get the octal representation. Now comes the octal to hexadecimal, same thing. So first to convert the octal to binary and then convert the binary to hexa. So first the octal to binary means replace each and every octal number by 3-digit binary number. And then after that I wanted to group in this manner with a 4-bit binary and then replace that 4-bit binary with hexadecimal. So we are going to get the finally hexadecimal. So for hexadecimal to octal, I wanted to first to convert hexadecimal to binary and then convert binary to octal. For octal to hexadecimal, convert octal to binary and then binary to hexadecimal. So this is the process that you always have to keep in your mind if you want to convert a data from one number system to the other number system. So let me tell you one more important concept which is called as the R-1's complement and the R's complement. So I already told you for any number system of radix R, there will be only 2 complements. There will be only two complements only which are going to present, which is R-1 complement and the R complements. So only these 2 complements are going to present for any number system of radix R. So therefore here for any number system of radix R, we are going to get R minus 1 complement and the R complement. So for any number system, of radix R, so we are going to have only R minus 1's complement and the R's complement. Suppose for binary and only 2 the radix is equal to 2, so R is equal to 2, so 2 minus 1 is 1 and 2, so 1's complement and 2's complements are going to present. Whereas for octal number system, the radix is equal to 8, so therefore we are going to have the 7's complement and the 8's complement. Similarly for decimal number system, the radix is equal to 10, so 1 is equal to 10, so you are going to have the 9's complement and the 10's complement. And for hexadecimal number system, and only to your hexadecimal system, the radix is equal to 16, so we are going to have the 8's complement and the 16's complement. 8's complement is 15, so 15's complement or 8's complement and the 16's complement. So these are the complements which are going to present for each and every variation. So for any number system of radix R, so we are going to have only two complements, only two methods of complements are present, which are R minus 1 complements and the R's complements. So for binary you are going to get the 1's complement and 2's complement, and for octal you are going to get the 7's complements and the 8's complement, and for decimal you are going to get the 9's complement and the 10's complement, and for hexadecimal you are going to get the 10's complement and the 16's complement. So now listen carefully how to do the procedure for R minus 1's complement and R's complement we are going to study. So for R minus 1's complement, write maximum number in that given base. So write maximum number in that given base and subtract given number from it. So write maximum number in the given base and subtract given number from it. Suppose basically they are given some number. Suppose for a radix, suppose if we consider general number system of radix R. So they are given some number in that number system. Then I want to find what is the R minus 1's complement. So first thing is here, first we have to write the maximum number in that base system. In the base system, you will write the maximum number with the corresponding digits. Suppose if they are given 3 digits, so with respect to 3 digits, we have to write the maximum number. And now subtract whatever the number they are given from this maximum number, and whatever the result that you are going to get, it is called as the R minus 1's complement. So write the maximum number in the given base and subtract the given number from it. Then this is called as the R minus 1 complement. So suppose in the question they are giving for some radix, for some number system, radix R, they are given some 3-digit number. So now you have to, for this 3-digit, you have to write the maximum number in that number system with the maximum values. Then you have to subtract the given number from the maximum value, and whatever the value that you are going to get, it is called as the R minus 1's complement. So write maximum number in the given base and subtract given number from it, it is called as the R minus 1's complement. So now for R's complement, write R minus 1's complement and then add 1 to the least significant digit or rightmost digit. So see, I already told you have to see whatever the value that you are going to get in R minus 1's complement. Now you have to add the plus 1 to the least significant bit or the least significant digit or the rightmost digit. Rightmost digit means I already told you one important point. So now you can see clearly here. Suppose it's a small example, there is a number like this 011.001. So now we can say the least significant digit or the rightmost digit is B. So for this number we have to add the plus 1. Suppose let me assume this is some R minus 1 complement number we have got here. Then we have to add plus 1 to this one, which is the rightmost digit. So this is the rightmost digit or the least significant digit. So for this one, we have to add the 1, and whatever the result that you are going to get, it is called as the R's complement. So whatever the result that you are going to get, it is called as the R's complement. So this is the thing that you always have to keep in your mind. So we can say basically, so whatever the number that you got from the R minus 1's complement, then you have to add the 1 to the least significant digit or the rightmost digit. The result is called as the R's complement. So this is the part that you always have to keep in your mind. So let me listen carefully. R minus 1's complement and R's complement. So for any number system, there are two complements which are the R minus 1's complement and R's complement. So R is the radix or base of a number system, or is called the radix or the base of a number system. So for binary, the radix is equal to 2, so we are going to get 1's complement and 2's complement. For octal number system, the radix is equal to 8, so we are going to get 7's complement and 8's complement. And for decimal number system, the radix is equal to 10, so we are going to get the 9's complement and 10's complement. And for hexadecimal number system, the radix is equal to 16, we are going to get x complement and 16's complement. So for r minus 1's complement, so write the maximum number in the given base and subtract the given number from it. So whatever the result that you are going to get is called as the r minus 1's complement. And for r's complement, so write the r minus 1's complement and add 1 to the least significant digit or rightmost digit. Whatever that value is not from the r minus 1 complement, you have to add 1 to the least significant digit with the rightmost digit, and the result is called as the r's complement. So this is something that you always have to keep in mind. We are going to discuss about the arithmetic circuits. So arithmetic circuits basically, we are going to see the different types of arithmetic circuits, each and everything that we are going to study. The first thing is called as the half adder. Half adder means we can say clearly, so this is basically half adder. It has only two inputs, A and B. So if you add these two binary inputs, then we are going to get a certain answer and also carry. So the output is basically sum and a carry. So basically in this half adder, we are going to have two binary inputs. So in this half adder, your input has two binary inputs. Then we are going to basically the arithmetic operation we are going to do. This the summing we are going to do. Add means basically it is going to do the addition. So half means only two inputs. So half means only two binary inputs. Add means doing the summation. So if you add these two binary inputs, you are going to get a sum and also carry. So inputs are A and B and output is sum and carry. Sum means yes, carry means C. So now we will see what is the truth table. So for AB, you can have 4 combinations if the input has n variables. Then we are going to get 2 to the power of n combinations. So as there are 2 inputs, so 2 to the power of 2 is equal to 4 combinations 0, 0, 0, 1, 1, 0 and 1, 1. Suppose if 0 and 0 is there, what is the summation? 0 plus 0 is 0, the carry of 0, and 0 plus 1 is equal to 1, the carry of 0, 1 plus 0 is equal to 1, the carry of 0, 1 plus 1 is equal to 2, so therefore sum is equal to 0, carry is equal to 1. So this is the way that you are going to get the truth table. So this is the sum we are going to get and this is the carry we have to get. So now we have to build the circuit. So if you see clearly the S is, you can see whenever if these inputs have a odd number of ones, then the output is 1. So you can see clearly for this case and this case, the number of inputs are having odd number of ones. So output is equal to 1. So S is equal to basically we can be in terms of the sum of product SOP, which is A bar B plus A B bar is equal to A XOR B. Whereas C, you can see clearly this is equal to A into B. So only for this case it has 1. In the remaining all the cases it is 0. So C is equal to A into B. So therefore S is equal to A XOR B is equal to A bar B plus A B bar. And C is equal to A into B. So now we have to build a circuit. So we have to basically build this half adder. So you can see clearly we are building the half adder using the XOR and the AND gate. So we are going to choose the XOR gate and the AND gate. So by this we are going to build the half adder. So inputs are A and B. S is equal to A XOR B. So XOR gate. So A XOR B means S is equal to A XOR B. And what is the carry? Carry is equal to A into B. So A into B. So this is the input C is equal to A into B. So we have this is basically an half adder. So we have built the half adder using an XOR gate and using an AND gate. So we need only one XOR gate and we need only one AND gate. Then S is equal to A XOR B and C is equal to A into B. So if A and B are the inputs, summation is equal to A XOR B and carry is equal to A into B. So this is the circuit that we are going to get for the half adder using the XOR and the AND gate. So now suppose if you want to build the half adder using the 2 NOR gate and one AND gate, how we are going to choose? Then you can see clearly. So this is the way that we have to build the 2 XOR gates. So 2 XOR gates you have to keep. So now we are going to build the alpha using the two NOR gates and one AND gate. So you can see clearly, so this is one NOR gate and this is another NOR gate. Here, so this is A and B. Here, this is the input is from here to here and this is input from here to here. So this is sum and this is carry. So we can see we need two NOR gates and one AND gate. So this is a circuit diagram. If you want to build an half adder using a two NOR gate and one AND gate. So C is always equal to A into B and this is equal to A XOR B. So A XOR B means A bar B plus A B bar that we can get with the help of these two NOR gates. This is the connection that you always have to keep in your mind. Even if you want to simplify also, you simplify the same thing that you are going to get. Even if you do a simplification, still you are going to get the same result. So this is another type of view. Suppose if you want to build the half adder using the NAND gate serial. Suppose if you want to build the half adder using the NAND gate serial, then I already told you for XOR we need 4 number of NAND gates. So if you want to build an XOR, we need 4 number of NAND gates. So you can see this is AB, so this is a NAND gate. So here you are taking like this and here you are taking like this. So like this you have to see. So this I already told you. If you want to build an XOR gate, if you want to fill an XOR gate, so if you want to fill an XOR gate, so if you want to basically build an XOR gate, we need 4 number of NAND gates, 4 number of NAND gates in this manner. So if you see clearly, what is this output? Here A and B, here is AB all bar, but we need C is equal to AB, so from here we have to take another NAND gate. So now we are going to get C is equal to AB. So total how many number of NAND gates are required? 1, 2, 3, 4 and 5. So 5 number of NAND gates are required if you want to build a half adder. So here you are going to get the sum, here we are going to get the carry. So here we are going to get the sum and here we are going to get the carry. So this is an important thing that you always have to keep in your mind. So if you want to fill an half adder using NAND gate serial, we require 5 number of NAND gates. Out of these, 4 are required to build the XOR gate and these two NAND gates are required to build this we can say AND gate. So 4 number of NAND gates are required to build the XOR gate and these 2 NAND gates are required to build the AND gate. So totally we are going to get 5 number of NAND gates. So this is a very important thing that you always have to keep in your mind. Suppose if you want to basically build the half adder using NOR gates alone, if you want to build the half adder using NOR gates alone, these things I already told you, but now I already told you if you want to build an AND gate using NOR gates, then we require 3 number of NOR gates. So these things I already told you. So if you want to build an AND gate, then we require 3 number of NOR gates. The remaining thing was same as this previous case. So total 1, 2, 3, 4, 5. So 5 number of NOR gates are used to require to build an half adder to get a sum and also to get the carry. So this is a very important point that you always have to keep in your mind. So 5 number of NOR gates are required to build an half adder and 5 number of NOR gates are required to build an half adder. So this is the point that you always have to keep in your mind. So we need 1 XOR and 1 AND gate here for the circuit. But here we require 2 NOR gates and 1 AND gate. Here we require 5 number of NAND gates. Here we require total 5 number of NOR gates. So these are the different type of circuits to build an half adder. The function is same for each and everything, just the way of building it is different. So now we discuss about the half subtractor. Half subtractor means, I already told you half means the number of inputs are only 2 binary inputs. So now we are going to do the subtraction. So this is called as a half subtractor. So what are the output that we are going to get basically, here we are going to get a subtraction A minus B and also borrow we are going to get. B is called as a result and B is called as a borrow. So I already told you, if number of input variables are n, you are going to get number of combinations are to the power of n. So A and B are the inputs. So 2 inputs which you are going to get to the power of 2 4 combinations 0 0 0 1 1 0 1 1. So now the result is B and the borrow is B. So 0 minus 0 is equal to 0. The borrow of 0 minus 1 if you want to subtract 0 minus 1, definitely you need to take a borrow. So borrow is 1. So 1 0 is nothing but 2. 2 minus 1 is equal to 1. So this is the 1. Similarly, 1 minus 0 is equal to 1 with the borrow of 0. 1 minus 1 is equal to 0 with the borrow of 0. So this is a point that you always have to keep remember. See here 0 minus 1, you can't do subtraction. So you have to take a borrow. So take a borrow of 1. So 1 0 is nothing but 2. 2 minus 1 is equal to 1. So we are going to get here 1. So this is the way you are going to get the result and the borrow. So this is called as A minus B and this is the borrow. So now I want to get the expression in terms of the SOP. If you want to have the expression in terms of SOP, you have to take only the 1 terms. For 1 term, this is A bar B and here A B bar. You will do the summation. So A bar B plus A B bar is nothing but A XOR B. And for borrow, you will see clearly only for 1 term, the only one has only for one sequence, which is 0 and 1. So the SOP form is nothing but A bar B. So B is equal to basically A bar B. So now we have to build a circuit of this OR subtractor. So OR subtractor we are going to build using one XOR gate and one AND gate. So you can see clearly here, this is B is equal to A XOR B. So this is A and this is B, which is basically B is equal to A XOR B. But now we have to do A bar. A bar means you have to keep your NOT gate. And here we are going to get A bar and this is B. So output B, this value is equal to A bar into B. So this is basically with the help of one XOR gate, one AND gate and one NOT gate, we are going to build an OR subtractor. So this is a circuit diagram. We are going to get, if you want to build an OR subtractor using this one XOR gate, one AND gate and one NOT gate. Suppose if I want to build OR subtractor using the NOR gates alone. Suppose if I want to build the OR subtractor using the NOR gates alone, then when I already told you, we require 5 number of NOR gates in order to build an XOR gate. I already told you, we need 5 number of NOR gates to do the XOR gate. So 1, 2, 3, 4 and 5. So B is nothing but A XOR B. So B is equal to A XOR B. But I want B. So this is basically, if you take the output from here, B is nothing but we are going to get A bar B. See, basically we can do a simplification also. We are going to get the same result. If you have done just the simplification up to here, you are going to get the same result. B is equal to A bar B. So how many number of NOR gates we require? 1, 2, 3, 4, 5. So total 5 number of NOR gates are required in order to build the OR subtractor. So total 5 number of NOR gates are required to build the OR subtractor. Suppose if I want to build the OR subtractor using the NOR gates alone, then how to do this one? I have already told you, if you want XOR gate, we require 4 number of NOR gates, 1, 2, 3, 4. So output is equal to B is equal to A XOR B. But B is nothing but A bar B. So we will take from here. Then B is nothing but A bar B. So you can cross check also. You are going to get the output B is equal to A bar B. So we can say total how many number of NAND gates? 1, 2, 3, 4, 5. So 5 number of NAND gates are required. 5 number of NAND gates are required to build and OR subtractor. So 5 number of NAND gates and 5 number of NAND gates are required to build an OR subtractor. So this is a point that you always have to keep in your mind. So now we will discuss about the full subtractor. Full adder. So now we are going to study about the full adder. Full adder means I already told you, if the number of inputs are 3, if the number of binary inputs are 3, it is called as a full adder. Adder means doing the addition. So we are going to do the binary addition of all these input variables. It is called as a full adder. So resultant we are going to get a sum and also carry. So now, listen carefully. As the number of input variables are given, we are going to get 2 to the power of n combination. As the input variables are n is equal to 3. So 2 to the power of 3 is equal to 8 combinations. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, and 3, 1. So this is a combination that you are going to get. Now 0 plus 0 plus 0 is equal to 0 with the carry of 0. 0 plus 0 plus 1 is equal to 1 with the carry of 0. 0 plus 1 is 1, 1 plus 0 is 1, the carry of 0, 0 plus 1 is 1, 1 plus 1 is 2, so therefore sum is equal to 0 and carry is equal to 1. Here 1 by 0 is equal to 1, 1 by 0 is equal to 1, so here you're going to get sum as 1, the k of 0, 1 by 0 is equal to 1, 1 plus 1 is equal to 2 is 0 and 1. So now here 1 plus 1 is equal to 2, 2 plus 0 is equal to 2 plus 0 is equal to 2, so therefore this is 0 and 1. And here 1 plus 1 is equal to 2, 2 plus 1 is equal to 3, 3 means a decimal in the binary format 1 1, so 1 1 you are going to get. So this is a point that you always have to keep in mind. So now we have to build this summation and also we have to build this carry from these inputs. So if you see clearly here for the summation, I already told you only for odd number of ones. Only for odd number of ones you are going to get the output as 1 and in the remaining cases you are going to get 0. This is basically an XOR gate, A XOR B, B XOR C. So A XOR B XOR C is called as the summation because only for odd number of input number of ones we are going to get the output as 1 and the remaining case output is 0. It is basically XOR. So A XOR B XOR C. Now see, I already told you I am going to consider only the SOP formulas only for 1 I am going to write the expressions. So therefore here it is basically A bar B C and here it is basically A B bar C and here A B C bar and here A B C. So if you simplify this in terms of the K naught, if you do a simplification in terms of K naught, finally we are going to get C is equal to AB plus BC plus AC. So this is the expression that we are going to get if you do a simplification using the K naught. Or you can also get another expression which is AB plus C into A XOR B. So these are the two things that we can get with the help of K naught. Either this one or this one, it is up to you which one you prefer. So this is one expression and this is also another expression. So both these expressions that you are going to get from the K naught itself, which is AB plus BC plus C or AB plus C into A XOR B. So any of this expression you can use to get the result. So this is an important point that you always have to keep in mind. So now I want to get in terms of the standard format of the SOP form sigma. Sigma is called as basically you can say sigma means summation, sigma means summation. So therefore sigma means I already told you in SOP format we are going to use the sigma, whereas in the previous we are going to use the pi. Pi means point. So here sigma terms means we have to choose the small n. Small n terms means we are going to choose a small n. You can see clearly this is n0, n1, n2, n3, n4, n5, m6 and m7. So you have to choose only those numbers where we are going to get 1, which is 1, 2, 4 and 7. Like n0, n1, n2, n4 and m7 is 1 to 4, 7. These corresponding terms you are going to get as a 1 term. So only those things we will take and we have to add here. Similarly for carry, so you can see clearly you have to choose only those 1 terms which has the corresponding 1. So this is basically 1 term, third 1 term, okay, 0, 1, 2, 3, third 1 term, fifth 1 term, sixth 1 term and seventh 1 term. So here n comma 3 comma 5 comma 6 comma 7. So this is basically the standard form of writing the sum of product. Sigma means summation, pi means product. So this is the important thing that you always have to keep in mind. So now with the help of these two expressions, we are going to build a circuit for this full adder. So you can see clearly it's the inputs A, B and C. In order to A XOR B XOR C. See I have 2 NOR gates. We have to build this functionality. So therefore this is A XOR B and this is basically C. So A XOR B XOR of C. So this is the sum. So this is the one XOR and the other XOR. So because we have only 2 input XOR. So if you have 3 input it is well and good. You need only 1 XOR. But you have 2 inputs XORs only. So you require 2 number of XORs. So this is the output is A XOR B and this is C. So therefore finally this is equal to A XOR B XOR C. Then what is the value of C? C is equal to AB. So this you are going to get AB and here you are going to get BC here and here you are going to get CA. So therefore you have to add all these things. So we need a OR gate. So C is equal to AB plus BC plus CA. So for AB we need 1 AND gate. For BC we need 1 AND gate. For AC we need 1 AND gate. For summation we need 1 OR gate. So this is a circuit. We are going to require XOR gates, AND gates and OR gate. So 2 XOR gates, 3 AND gates, 3 AND gates and 1 OR gate. So this is the circuit diagram that we are going to choose here. Suppose if you want to build in terms like this, like if you want to fill it in the terms of like this, you can see clearly this is basically 1 full one half adder. This is basically one half adder, and this is another half adder, and here we need a OR gate. So basically, if you want to basically build a full adder in terms of half adders, then we need two half adders and one OR gate. So listen carefully. If you want to build a full adder, then we require two half adders and one OR gate. So this is a very important point. So you can see clearly, this is we are going to get the same expression. If you simplify the circuit, you are going to get the same result. Same result that we are going to get. Summation is equal to AX and DX or C, and C is equal to AB plus BC plus CA. So you are going to get the same result, but the way of executing is different. So this is one half adder, another half adder, and one OR gate. So if you want to build a full adder in terms of half adders, then we require two half adders, one OR gate. Suppose now if we want to do this full adder only in the terms of NAND gate, then you can see clearly this half adder I am replaced by total and NAND gates only. And here this half adder also I am replaced by total NAND gates only. Then I kept here one more NAND gate. So therefore this circuit you can see this is one half adder and this is one half adder, and here one more NAND gate I am taken. So now if you see clearly, I have built the full adder in terms of NAND gates alone. So this is one half adder, another half adder. So this is one more NAND gate. So total number of NAND gates are present 1, 2, 3, 4, 5, 6, 7, 8, 9. So total number of 9 NAND gates. 9 NAND gates are required to build the full adder. See, the way of executing the different circuits is different, but the procedure is same. We are going to get the same results. But the circuits, the making of circuits for different elements are different, but the process is same. We are going to get the same result. So total 9 number of NAND gates are required to build this full adder. Suppose if you want to build only in the terms of NAND, only in the case of NOR gates. Suppose if you want to build the full adder only in the terms of NOR gates, here there is basically one half adder, another half adder, and another NOR gate. So basically you are going to get the same result. S is equal to AX or BX or C, and C is equal to AB plus BC plus CA. So this is also one type of way of executing the full adder. So you can see clearly 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 number of NOR gates. 9 number of NOR gates are required to build this full adder. So 9 number of NOR gates are required to build the full adder. So we can say a full adder can be implemented only with the NAND gates of 9, or a full adder can be implemented with the help of NOR gates of total 9. So these things we always have to keep in your mind. Now we are going to discuss about the full subtractor. As I already told you, full subtractor means here full means we are going to give the 3 binary inputs A, B and C. So subtractor means we are going to do the subtraction operation. So we are going to do two resultants. One is called resultant and the other is called as the borrow. So the operation which we are going to do is A minus B minus C. So first we are going to do the subtraction of A from B, and then the resulting order that we are going to get, again we are going to subtract from C. So this is the operation that we are going to do here. So here as there are 3 inputs, so 2 to the power of 3 is equal to 8 combinations. So A, B, C, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1 double 0, 1 0 1, double 1 0 and 1 1 1. So you can see clearly then what is the B, and I already told you the operation is A minus B minus C. So 0 minus 0 is 0, 0 minus 0 is 0, so therefore we are going to get B as 0 and B as 0 because 1 is 0. So now 0 minus 0 is 0, 0 minus 1 is, so if you want to separate 0 minus 1, definitely you take a borrow of 1. So 1 0 is nothing but 2, 2 minus 1 is equal to 1. So therefore, this is a B is equal to 1 and B is equal to 1. Again 0 minus 1 is nothing that we can't do. So we will take a borrow of 1. So 2 minus 1 is equal to 1. 1 minus 0 is equal to. So 0 minus 1. So we can't do the subtraction. So definitely you will take a borrow. So 2 minus 1 is equal to 1. 1 minus 0 is equal to 1. So 1 is b is equal to 1 and 1 is equal to 1. Again 0 minus 1. So definitely we have taken value of 1. So 1 0 is nothing but 2. 2 minus 1 is equal to 1. 1 minus 1 is equal to 0. So this is 0 and 1 is 1. So 1 minus 0 is equal to 1. 1 minus 0 is equal to 1. So 1 minus 0. And 1 minus 0 is equal to 0. 1. 1 minus 0 is 1. 1 minus 1 is 0. So 0, 0. Here again 1 minus 1 is 0. 0. 0 minus 0 is again 0 and 0. And 1 minus 1 is 0. 0 minus 1 is take a bar of 1. So 2 minus 1 is equal to 1 and 1. So this is the output B and this is the output B that we are going to get. And what I told you, I am going to write in terms of the mean terms. So therefore here you can see clearly I want to write in terms of standard format. So sigma n, this is n1, n2, n4 and n7. So these are the mean terms which are having the as one values. So you have to write the sum of product. Sum of product means sigma n. So these mean terms that you always have to do the addition of these corresponding mean terms. Then B, here also we are going to take the mean terms. So you can see clearly it is having 1 for en1, en2, en3 and en7. Only these variables have the output as 1. So we are going to write the output expression in terms of mean terms on SOP. So sigma mean terms 1, 2, 3, 7. So all these mean terms that we have to add. So we are going to get the output for B and output for B. So this is a we are going to get. This is basically in terms of the standard format. Then what is the value of B? B is nothing but a value to you. If you see carefully, only for odd number of inputs means the more the input variables as the number of one values are odd, then only the corresponding output is 1. So in the number of inputs, if the number of input variables which are having odd number of ones, then we can say that output is 1. So we can say simply B is nothing but A XOR B XOR C. So now similarly, if there is a B here, so what is if you do a cleanup and you do a simplification, finally we are going to get like this, which is A bar C plus A bar B plus B C. So simply we can write another format also, which is A bar B plus A XOR B into C. So either you can write this one or either you can write this one, and then we are going to get the same result. So these are the two things that we are going to get from the K-map or K-map map. So B is equal to A bar C plus A bar B plus B C is equal to A bar B plus A XOR B into C. So these are the two expressions that we are going to get from the K-map. So now with the help of these outputs, we are going to build this full subtractor from the networks from the base that we already know. So now you can see clearly, as I already told you, I am going to build this circuit. So if you see clearly, this is B is equal to A XOR B XOR C. So I have two NOR gates with the input of two inputs. See, I have two basically XOR gates. If I have two XOR gates and each having a two input, so I need two number of these things. So this output is equal to this input is A and B. So output is A XOR B. Again there is a C. So A XOR B XOR C. So we are going to get B as A XOR B XOR C. So now here I am going to use AND gate here, AND gate here, AND gate here, and now I am going to the summation. So we are going to get here. This is I am going to keep in place of A, and I am going to keep a NOT gate. So here we are going to get A bar into here, A bar into B we are going to get here, and this A bar into C we are going to get here, and here this is B into C. So with the addition of all these things we are going to get B is equal to A bar C plus A bar B plus B C. So I am going to circuit based on this expression. So this is the one of the thing that we are going to get. So this is circuit diagram for the full subtractor. Suppose if I want to do in terms of half subtractors, then what I am going to do? See, if you want to build a full subtractor from the half subtractors, then we need two half subtractors with a OR gate. So again, if you do simplification, same result we are going to get. B is equal to A XOR B XOR C, or B is equal to A bar C plus A bar B plus B C. So this is the point that you always have to keep in your mind. So therefore we are going to get, simply if you want to build a full subtractor, we need two half subtractors with a OR gate. So this is a very important point that you always have to keep in your mind. Now we will discuss the other important concept. Listen carefully. This is called as the parallel adder or the repeat carry adder. So it is also called as the parallel adder or the repeat carry adder. So parallel adder or repeat carry adder. Suppose for n bit parallel adder, what is the thing that you always have to require? So we have already told you it's a parallel adder or repeat carry adder. So for n bit parallel adder, we require n-1 full adders and 1 half adders. So for n bit parallel adder, we require n-1 full adder and 1 half adder. Or simply we can also use n full adders or n full adders, and here 2n-1 half adders plus n-1 OR gates. So these are the things that you always have to require. So for n bit parallel adder, we require n-1 full adder plus 1 half adder, and also or we can go for n full adders or 2n-1 half adder plus n-1 OR gates. So these number of things that we require in order to build a n bit parallel adder. We are going to require for the n bit parallel adder, or we can say, so for n bit parallel adder, we require n-1 full adders and 1 half adder. So we can say clearly here n-1 full adder plus 1 half adder. I already told you, if you want to implement 1 full adder, we require 2 half adders plus 1 OR gate. So if you want to implement 1 full adder, we require 2 half adders plus 1 OR gate. So in simplification, this is n-1 into 1 half adder requires 2 half adders plus 1 OR gate plus 1 half adder. So if we multiply this one, n-1 inside, we are going to get 2n minus 2 half adders plus n-1 OR gates plus 1 half adder. So if you do the multiplication of if you do the addition of these two things, we are going to get 2n minus 1 half adders plus n-1 OR gate. So simply we can say that finally the n, we can say that the n bit parallel is going to require n-1 full adders plus 1 half adder or 2n minus 1 half adders plus n-1 OR gate, because 1 full adder requires 2 half gates, 2 half adders plus 1 OR gate. So with the help of this concept, we are going to get the simplified of this expression. So now finally we can say the parallel adder is also called as a repeat carry adder. So for n bit parallel adder, we require n-1 half adders plus 1 half adder or simply n full adders. So 1 full adder is nothing but we are going to replace 1 full adder we can give with the help of 2 half adders plus 1 OR gate. So if we do simplification, we are going to get finally 2n-1 half adders plus n-1 OR gates. Suppose I want to build a 4-bit parallel adder. Suppose if I want to build a 4-bit parallel adder, then we can see clearly here. So this is the first adder, second adder, third adder and the fourth adder. So let me add this is FA0, FA1, FA2 and FA3. So like that I am going to assume this is the first adder, second adder, third adder and fourth adder. So I am going to count in a parallel fashion. So this is A0, B0, A1, B1, and this is A2, B2, and this is A3, B3. So you can see clearly this is A0, B0, this is A1, B1, this is A2, B2, and this is A3, B3. But it's a n bit parallel adder, so therefore here, if the full adder means input should be 3, so therefore here, initially, so this input I am going to give this as the 0 input. Initially I am going to give this as the 0 input. So this is the other input I am going to take as a 0. So then for this there will be output, 2 outputs we are going to get, one sum and it's a carry. So this carry again we are going to go to here. Again we are going to get sum and a carry. Again this carry we are going to give it to here. Again we are going to get sum. Again we are going to give the carry to here. So again we are going to get sum and carry. So finally we can see that the carry is traveling from here to here. We can see the carry is traveling like this. So the carry is always traveling like this. So we can say this is called as the repeat carry adder, means the carry is traveling from the full adder 0 to full adder 3 like this. So it is traveling like this. So because of this reason, we call it as a repeat carry adder, means the carry is traveling in this fashion from one adder to the another adder. So the carry is traveling from one full adder to the other full adder in this fashion. So because of this reason, it is called as the repeat carry adder or the parallel adder. So here we are going to use all the full adders only. We are going to use all these are the full adders. So definitely the input here should be always equal to 0. The input here should be always equal to 0, because here we have to add only these two things but not the other one. So this input should be always equal to 0. Let me assume this input is 0. So I am going to assume this input is equal to 0. So for every full adder, we are going to have 3 inputs and 2 outputs. And the 3 inputs are A0, B0, and one is a carry we are going to get, and here we are going to get basically SM and also carry. So this carry is going to be this number. So I wanted to for one full adder, I wanted to know one full adder is nothing but just now we have seen for one full adder, I wanted to know what is the S is equal to A observe B observe C, and C is equal to AB plus BC plus CA. So this is a one full adder circuit, means the circuit which is inside this one full adder, this is the circuit that we are going to present for each and every full adder circuit. So S is equal to where this is input is A and B, so here is A observe B, here is C, so A observe B observe C. So this is AB, this is BC, and this is CA. So it will be addition of all these things here, C is equal to AB plus BC plus CA. So this is the each and every full adder circuit we are going to get. So we can say carry is traveling from one full adder to the full adder in this fashion. So because of this reason only, it is called as the ripple carry adder. So this is A1 B1, A1 B1, A2 B2, A3 B3. This is S0, S1, S2, S3, and this is the carry C4. So this is the carry C4. This is the thing that you always have to keep in your mind. So this is basically C1, this is basically C2, this is basically C3. So this is C4. So this is C1. So this is C1, this is C2, this is C3, and this is C4. So A1 B0, A1 B1, A2 B2, A3 B3, S0, S1, S2, S3. This C0 is equal to 0, this is C1, this is C2, this is C3, and this is C4. So this is the point that you always have to keep in your mind. So now we discuss some important points regarding this parallel adder of the ripple carry adder. The rate of addition means number of complete additions in 1 second, means the number of complete additions in 1 second, how many which are done, it is called the rate of addition, means the number of complete additions in 1 second is the 1 by, it is a 1 by delay for one complete addition. It is 1 by delay for one complete addition. So delay for one complete addition is equal to N-1 TPD carry plus maximum of TPD sum of TPD carry. So very important formula that you always have to keep in mind. The rate of addition means the number of complete additions which are taken place in 1 second, which is 1 by delay for one complete addition, which is 1 by delay for one complete addition, which is the delay for one complete addition is equal to this much amount of time is taken in order to complete the one addition. So this much amount of time is taken in order to complete the one addition. So if you want to find the rate of addition, the number of complete additions in 1 second is nothing but 1 by delay for one complete addition. So delay for one complete addition is equal to N-1 into TPD carry. So N-1 TPD carry plus maximum of the proportional delay of the sum, the proportional delay of the carry. So this is a very important point that you always have to keep in your mind. It is N-1 into the propagation delay time of carry plus it is maximum value of the propagation delay of the carry, the propagation delay of the sum. So this is a very important thing that you always have to keep in your mind. So therefore simply we can say here the rate of addition is the number of complete additions that are going to take place in 1 second is equal to 1 by time taken for one complete addition, or we can say delay for the one complete addition, or time taken for one complete addition, or simply we can say time taken for one complete addition or delay for one complete addition is equal to N-1 into the propagation delay of the carry plus the maximum value of the propagation delay of the carry, the propagation delay of the sum. So this is a very important point that you always have to keep in your mind. Now we are going to study about the other new concept which is called as a carry look aid adder or full adder. Means we are going to study about the carry look aid adder for the full adder. So now you can see clearly carry look aid adder for the full adder, which is, so basically we are going to have 3 inputs A, B and C. So now here basically we are going to build a circuit because in the previous circuit in the input parallel adder then we are going to take a lot of time. So we are going to take a lot of time because the carry has to travel from the first full adder to the nth full adder. So it is taking a lot of time. Instead of doing this thing, we are going to go for the carry look aid adder for full adder. So therefore it will take less time, but the circuit is very complex when compared to previous one. So now we are going to get the result in a very faster manner when compared to previous one. our circle is very complex. So we will discuss something more about this one. So carry look add adder for full adder we are going to do this one. So I already told you these are the for full adder input we are going to have the three inputs A, B and C. So I already told you here for a full adder what is the output is S is nothing but we are going to get A XOR B XOR C and also C is equal to AB plus BC plus CA. So we are going to build a circuit in this fashion. So in this fashion we are going to use two alpha gates and also we are going to use one OR gate. So like this we are going to do. So we are going to get the same result as the previous one. This S is equal to A XOR B XOR C and this carry is called as the we are going to get which is AB plus BC plus CA. Here A, B are the inputs and C is the carry we are going to get from the previous full adder. So C is the carry which we are going to get. C is the basic input to this full adder from the previous full adder circuit. So therefore this is the important thing that you always have to keep in the mind. So this is the ABC input, or you can say A, B, C, and this is the basically here this PI and this GI and this is SI and this CI plus 1. So this is the SI output plus this is the CI plus 1 carry we are going to get here. So now what is the value of GI? GI is equal to, you can see clearly input is A and B, which is GI is equal to A into BI. So therefore G is equal to A into BI. Similarly what is the PI? PI is equal to A XOR of BI. So therefore PI is equal to A XOR of BI. Then what is the value of SI? SI is nothing but simply this PI XOR with CI. So therefore SI is equal to PI XOR with CI. So PI is nothing but simply I wanted to A XOR of BI. So we are going to get the same thing. So SI is equal to PI XOR of CI. Similarly what is CI plus 1? CI plus 1 is equal to simply we can say this is a PI and this is C. So PI into C plus GI. So PI into CI plus G is the CI plus 1. So this is the expression that you always have to keep in your mind. So GI is equal to A into BI and PI is equal to GI XOR of BI and SI is equal to PI XOR of CI and CI plus 1 is equal to PI CI plus GI. So GI is called as a carry generating term. So GI is called as the carry generating term. Because of this only we are going to get the carry. So GI is called as a carry generating term. So because of this only we are going to get the carry. So this is called as the carry generating term. And PI is called as the carry propagation term. So PI is called as the carry propagation term. So J is called as the carry generating term and PI is called as the carry propagation term. So this is a very important point. So PI is called as the carry propagation term and J is called as the carry generating term. So you can see clearly there is a J, there is a J here, there is a P, there is a P here. So like this you have to remember. So J is carry generating term and P is called as the carry propagation term. So now we can see, suppose we are going to go for the 4-bit carry look add adder. Suppose if you are going to use the 4-bit carry look add adder, then now we are going to get. So basically for each and every full adder, we are going to get each and every term. So therefore now we can see clearly for 4-bit carry, for 4-bit carry look add adder. So we are going to get P0, P1, P2, P3, G0, G1, G2, G3 and S0, S1, S2, S3. So for each and every one we are going to get like this P0, P1, P2, P3, G0, G1, G2, G3 and S0, S1, S2, S3. So P0 is equal to A0 XOR of B0, P1 is equal to A1 XOR of B1, P2 is equal to A2 XOR of B2 and P3 is equal to A3 XOR of B3. Similarly G0 is equal to A0 B0, G1 is equal to A1 B1, G2 is equal to A2 B2 and G3 is equal to A3 B3. Then S0 is equal to simply P0 XOR of C0, S1 is equal to P1 XOR of C1, S2 is equal to P2 XOR of C2 and S3 is equal to P3 XOR of C3. C0, so I already told you C0, this we are going to already available. So it is already available for the first full adder. Then what is C1? So if the substitute I is equal to 0, we are going to get C1 is equal to, I will replace I is equal to 0. So P0 C0 plus G0. So P0 C0 plus G0. Suppose if you want C2 plus keep I is equal to 1. So we are going to get P1 C1 plus G1. So C2 is equal to P1 C1 plus G1. But C1 is equal to the value substitute and simplification. We are going to get like this. It is P1 P0 C0 plus P1 G1 plus G1. Again C3 is equal to how much? P2 C2 plus G2. But C2 value we know substitute and simplify, we are going to get P2 P1 P0 C0 plus P2 P1 G0 plus P2 G1 plus G2. Similarly, C4 is equal to P3 C3 plus G3, C3 value we substitute and do simplification, finally we are going to get C4 is equal to P3 P2 P1 P0 C0 plus P3 P2 P1 G0 plus P3 P2 G1 plus P3 G2 plus G3. So these are the terms that we are going to get for C0, C1, C2, C3 and C4. C0 is already available, so we are going to get the terms for C1, C2, C3 and C4. So these are the points that you always have to keep in mind. So this is a carry, look, add, adder. So carry, look, add, adder for 4 elements. Now the previous one, it is taking a lot of time. We have to turn the carry from one folder to the folder. So it is taking a lot of time. So instead of that, we are going to do this complex circuit to make things very simple. So we are going to get the result in a very small amount of time. So now we are going to build a circuit. So you can see clearly carry, look, add, adder. So carry, add circuit, or simply we can say carry, look, add, adder circuit. So now same thing that we are going to apply here. Same what I told you, we are going to implement the 4-bit carry, look, add, adder circuit. So you can see clearly what I told you, these are A0, B0, A1, B1, A2, B2 and A3, B3. So now I already told you what is the P0. P0 is equal to A0 XOR B0. So we are going to get A0 XOR B0 here. And similarly G0 is equal to A0 B0. Similarly P1 is equal to A1 XOR B1 and G1 is equal to A1 into B1. So P2 is equal to A2 XOR of B2 and B2 is equal to A2 into B2 and P3 is equal to A3 XOR of B3 and G3 is equal to A3 into B3. So we are going to get P0 G0, P1 G1, P2 G2 and P3 G3. So C0 is already available and already told we are going to get this as basically C0. Initially we are going to get this is C0. So the default 0 is nothing but it is equal to 0. Because C0 is always equal to 0 that we are going to get, because it is a initially we are going to keep C0 as 0 because it is our input for the first order. By default we are going to keep it as 0. So therefore this is basically C0. So now this is C0. So this is the C0 we are going to take it as it is. So now as I already told you, now with the help of these things, with the help of P0 G0, P1 G1, P2 G2 and P3 G3, we are going to develop the C1, C2, C3 and C4. And I already told you C1 is nothing but P0 C0 plus G0. So P0 C0 plus G0. So C1 is equal to P0 C0 plus G0. So now C1 is nothing but we are going to get P0 C0 plus G0. I already told you. So we have to build a circuit like this. Here this is basically this is input is P0 and this is C0 and this is G0. We are going to do inputs like this P0 C0 and G0. So we are going to get C1 is equal to P0 G0 P0 C0 plus G0. Similarly what is the C2? C2 is nothing but I already told you P1 P0 C0. So this is P1 P2 and this is C0. So then this is P1 G0 and this is G1. So like this if you do this one finally we are going to get C2 is equal to P1 P0 C0 plus P1 G0 plus G1. Similarly C3 I already told you how to do input like this which is P2 P1 P0 C0. Here we are going to give which is P2 P1 G0. Here we are going to give basically I already told you this is called P2 G1 and this is here we are going to give G2. So like this we will do solution of all these things we are going to get C3. Then we are going to get the net resultant of C3 we are going to get. Again C4 I already told you P3 P2 P1 P0 C0 plus P3 P2 P1 G0 plus P3 P2 G1 plus P3 G2 plus G3. So with the help of these things, with the help of P0 C0, P1 G1, P2 G2, P3 G0, we are going to develop this C1, C2, C3, C4 from the above equations. So with the help of all these inputs, we are going to keep this mainly AND gates and OR gates. With the help of these inputs and these circuits, we are going to get the value of C1, C2, C3, C4 means here instead of calculating, instead of carrying the carry from one full adder to the other full adder, we are directly calculating the value of C1, C2, C3 and C4. So we are not traveling this carry from one full adder to other full adder, but we are directly calculating these values C0, C1, C2, C3, C4 from the circuits. So because of this, the time is very less, so we can get the very speed and we can get the result very fast. So now I already told you what is S0. S0 is equal to P0 X0 of C0. So P0 X0 of C0. S1 is equal to P1 X0 of C1. So P1 X0 of C1. And S2 is equal to P2 X0 of C2. So P2 X0 of C2. And S3 is equal to P3 X0 of C3. So P3 X0 of C3. Then the C4 we are going to take as it is. So this is the thing that we are going to get as an output. So we are going to get the result very fast. So we are going to get the result very fast when compared to any term adder or the ripple carry adder. So when compared to that, we are going to get the carry adder circuit is a complex, but we are going to get the result very fast because we are directly calculating the carry value C1, C2, C3, C4 based on these inputs very directly. So we are not traveling the carry from one circuit from one full adder to other full adder. So we are saving a amount of time. So we are going to get the result very fast. So this is the point that you always have to keep in your mind. So this is basically carry adder for the 4 bits. For the 4 bit addition, we are going to see here. So now let me tell you some important points regarding this circuit. For n bit, or you can say for n bit carry adder, full adder. So for n bit carry adder for the full adder, we are going to see the number of AND gates used inside carry circuit is equal to the number of AND gates used inside carry circuit. See, inside this carry circuit, we are asking the number of AND gates used inside carry circuit is equal to n into n plus 1 by 2. Because you can see clearly here we are going to use 4, here we are going to use 3, here we are going to use 2, here we are going to use 1. So for a 4 bit, here we have used 4 AND gates, here we have used 3 AND gates, here we have used 2 AND gates, and here we have used 1 AND gate. So if you add all these things, 4 plus 3 plus 2 plus 1. So it is basically, suppose for n bit, we are going to get n plus n minus 1 plus n minus 2 up to 1. So n bit is nothing but n plus n minus 1 plus up to 1 is equal to simply 1 plus 2 plus 3 plus up to 1 is equal to n into n plus 1 by 2. So therefore 1 plus 2 plus 3 plus up to 1 is nothing but n into n plus 1 by 2. So this is the number of AND gates which are required inside the carry ahead circuit. Inside this carry ahead circuit, we are going to get the number of AND gates are nothing but n into n plus 1 by 2. So number of AND gates used inside the carry circuit is equal to n into n plus 1 by 2. Number of OR gates used inside the carry circuit is equal to, so you can see n, because for 4 bit we have used the 4 OR gates. So for n bit we have to use the 4 n OR gates. So therefore the number of OR gates used inside the carry circuit is equal to n. So number of carry, we can say the number of OR gates used inside the carry circuit is equal to n. See, if all the logic gates, AND gate, OR gate, XOR gate. So we have used only XOR gate, AND gate and OR gates here. So XOR gate, AND gate and OR gates, only these gates which we have used. Suppose if all logic gates, AND gate, OR gate, XOR gate have same delay, same propagation delay, then to provide carry output delay, we require 3 TB. So basically what I am trying to say is that all the logic gates which are used in the circuits of AND gate, OR gate and XOR gate have the same delay, in how much amount of time required to get the carry results at 3 TB. So you can see clearly this is 1 TPD, this is a 2 PD, and this is a 1 TPD, another TPD and another TPD. So total 3 TPD. So within 3 TPD we are going to get the results for carry. So this is 1 TPD. Here another TPD, here this is another 3 PD. So if you add all these 3 TPDs, we are going to get 3 PD. So 3 TPD are required to get the results of the carry outputs. So therefore, if all the logic gates AND gate, OR gate, XOR gate have same propagation delay 3 PD, then to provide the carry output delay, we need total time of 3 PD. And then to provide the sum output delay, we need 4 TPD, because up to that is 3 PD, again we need one more. So therefore again plus 1 is nothing but 4 TPD. So this is 1, so 2, 3 and 4. So total 4 TPD to get the sum results, but to get the carry outputs we need 3 TPD. So this is a very important thing we always have to understand. This delay is independent of number of bits, but depends on number of levels. So you can say is basically depending upon the number of levels, but it is independent of the number of bits. No matter what are the bits, so it is only depending upon the number of levels, level 1, level 2, level 3 and level 4. So this delay is depending only on the number of layers, but it is independent of the number of bits. No matter how many bits that we are going to do the addition or subtraction, the time delay is independent. It is depending only on the number of levels. So irrespective of the input can be any value. The time to get the carry output is 3 per day and the time to get the sum output is 4 per day. So this is the point that we always have to keep in mind. So finally I can say that the number of AND gates, because of the number of AND gates used inside the carry circuit is equal to n into 1 by 2, and the number of OR gates used inside the carry circuit is equal to n if all the logic gates AND gate and OR gate and XOR gate have the same population delay. Going to get the into provide the carry output delay we are going to use 3 TPD, and then to provide the sum output delay we require 4 TPD. And this delay is independent of the number of bits, but depends only on the number of levels. So whatever this time delay for the carry output and the sum output, it is only depending upon the number of levels, but it is independent of the number of inputs. So this is the point that you always have to keep in your mind.